So first is the inclusion control. Basically, a clean steel is a misnomer. Basically, the steel, you cannot get a steel where there is no inclusion. Actually, there are several thousand inclusion per cubic centimeter in casting. And this inclusion basically affect the upstream and downstream processes as well as steel in the use when you are using the steel. Upstream processing, they affect by clogging the nozzle. In the downstream processing, like using the mechanical deformation, they can develop the weakness because of stress concentration. And finally, when you are using the steel, then they hamper the fading and the pollution property mechanical processing. So we have to control this inclusion. And what do we mean by the control? Basically, control has two aspects. First thing is that we can basically convert the deleterious inclusion like alumina inclusion. They are very deleterious in this sense because they are trying to form the cluster. Because they have a very high surface tension in the liquid, so alumina cluster, alumina part will come together and they make a cluster. Basically, they form a chunk or hair-like structure that basically when they come into the nozzle, they basically block the nozzle. So if you can modify this solid alumina inclusion to the liquid compound, then this problem is erased. So that is one control. Another control is that you have a lot of inclusion basically trapped in the liquid steel. You can payload their size and morphology such that they become this harmful. Okay. So conventionally, the calcium is used as an inclusion modifier. And just one modifying, what does it modify? Basically, you can see this is the alumina inclusion, the air inclusion, and vanillin sulfide also steamless. They produce a lot of anisotropy after rolling this structure, and after rolling also alumina inclusion looks like this. They are very hard. Basically, they cannot accept any energy. All the energy they transmit at the interface as a result, they act as a stress concentrator. But if you treat with the calcium, you can get a very
please dispense with that. Allow me to speak.
You can basically convert this inclusion to a very nice inclusion. It's called a partial inclusion, where you can get the calcium aluminate inside, and then the sulfide outside. And these inclusions are deformable also because this sulfide acts as a cushion. So when you give some energy during mechanical deformation, they can take the energy. Unlike alumina inclusion, they cannot take the energy. Or they transmit at the inclusion solid interface, matrix interface, they can act as a cushion. And that's why they are not very harmful into the practice. So basically the calcium injection, they are also a problem, and my research starts here because calcium is highly volatile and reactive. So you cannot easily dump on the top of the liquid still. You have to inject it, submerge it to the liquid still. How do they do? Basically, it is done by a cold ware. Cold ware is nothing but there's a hollow cylinder of cast iron, and then you can pack the cylinder with calcium powder, and they will look like a ware, just like this ware. And then by mechanical device, you can insert the ware. But thing is that in open system like steel, you do not know where the ware melts. Basically, ware should melt just at the bottom and release the powder such that it can get sufficient time for its assimilation into the liquid steel. So there requires a mathematical model. So we developed a mathematical model, and just this is the schematics of the cross section of the ware where you can insert it. So what happens is that when you have an overlying slag layer, first a slag shell basically formed over the casing. This is the casing, the slag shell formed, and then a liquid solidified there's a steel shell forms, and then the steel cell dissolved, and then the slag cell dissolved, and the casing melts, and finally the powder is released. So it is not a very simple thing. So, and also at the casing and slag interface, you have a contact resistance because they do not weight each other significantly. Okay. So based on that, we developed a model. It's a simply one-dimensional heat conduction model with the moving boundary model, not a very difficult model, very simple. And then we define different routes of melting. I will just discuss both that is by whether the slag is present or absent, or your superheat high and low. And I am just discussing about the route flow because it is more interesting result comes here. So when you have the slag and the low superheat, what happens, you can see this is the cold ware. and then first slag cell form, and over there the steel shell forms, and then the steel shell grows, then steel shell melt back. But before the steel cell completely melts, the slag cell inside melts because slag has a lower liquidity than that of the steel. Sorry if I said. So as soon as the steel, then the slag melts, the contact, that is the resistance vanishes because liquid slag completely weighs the casing, and suddenly there is a surge of heat flux. As a result, again the steel cells start growing, and that is called the secondary growth of the steel shell. And finally, that steel shell again melts, then the casing melts and the powder is released. Obviously, the presence of slag delays the melting, and by that time powder gets sufficiently hot, and their molten condition the bottle says. So some other important results I will talk about. So model, what the model can do, most interestingly it can do, that is where the wear melts and how much distance the wear travels before it melts. That is the things it can do. And there exists, obviously, if it is found that there exists an optimum speed at which the wear can penetrate maximum distance, because general conviction is there, higher the speed, higher will be the wear will penetrate, but another factor is there, because at higher speed, the heat transfer and the solid liquid thermal boundary layer also increases. So that tries to melt the wear faster. So there is two counteracting factors that means. And the presence of overlying slag obviously delays the melting. And it has been found that the wear melting is more sensitive to the spacing thickness rather than the wear diameter. And obviously the wear travels more distance with high carbon heat because the high carbon heat has low liquidity. So some industrial application that we have done, this model we have applied to wider steel, and their problem was not getting the stable casting because of nozzle clogging. So our idea is to convert the alumina inclusion into liquid product, like calcium aluminum. So what we did using this model, because you can see there is a wide range of parameters. Their wear speed changes from 110 to 280 centimeter per second, and bath temperature also widely. And for all these wide operating parameters, we calculate the distance traversed by the wear. And you can see, and also we have estimated the calcium recovery by measuring the calcium content before and after the wear addition. And we correlated this estimated calcium recovery with the distance traversed by the wear. And you can find, yes, the recovery is maximum when the wear melts just at the ladle bottom. And another thing you can find, most of the operating parameters, the distance traversed by the wear is more than the ladle bottom. What does it mean? Basically, the wear does not melt even after reaching the bottom. They can spiral and they can move up, and they can melt somewhere above there is an inside the bath, much above. So as a result, their recovery will be much less. So anyway, after we get this correlation, then another important factor is the calcium level in the bath. Because you can see from the binary diagram, COA to binary diagram, there exists a particular composition where the calcium aluminate a liquid. That is liquid at steel making temperature, 1600. Other calcium aluminate may not be liquid. So you have a particular Ca by L ratio which ensures the product will be liquid. So this is the range where when the inclusion composition is this, all the liquid product you will get, and you will not get that is your unstable casting because of nozzle clogging. So thing is that because we know we have calculated the resistance traversed by the wear at different parameters, and then corresponding recovery I know, and I know the initial aluminum content, so I can now predict for what is the amount of the wear addition that will make the calcium level just appropriate, and Ca to A ratio, L ratio should be in this range. So based on that, we have advised them that you inject this much of wear into the bath. So based on that, when they do that, after recommendation, we really find the inclusion composition down in this area, most of us, few of them may be outliers. So that way, and another implementation at Tata Steel, what we have done that time Boshak was working as a PGDC candidate. And here basically we see what is the, how much wear has to be added to produce a perfect inclusion. What is perfect inclusion? You can see where you can get a core shell inclusion with the sulfide in the periphery, and found this EDX mapping, elemental mapping, you can see there is a perfect sulfur. I do not know whether it is very clear or not. The perfect sulfur. So we found that this type of inclusion can be obtained at 150 meter per minute. That is below the speed of 200 meter per minute when recovery is maximum. So for a particular wear addition, calcium recovery is 20 to 35 at 200 meter per minute, but for making the proper inclusion, we need 150 meter per minute. Right? Basically, we will not consider this speed. Basically, we are considering this much of calcium. So at the average, if you take it is 17.5. So basically, the calcium level has to be reduced from 27.5 to 17.5, and this we can do simply by reducing the wear injection. And we should keep the speed 200 meter per second when the recovery is maximum. So if we do that, we found that really that is the wear addition is decreased. 100 meter wear we can save, and that amounts to around 33% saving. Okay, so now this is the inclusion. This is the last project, and this project was with the Center of Excellence in Advanced Manufacturing Techniques at Pattapu, and DHI supported a lot of funding there, and I also operated one of the project with the, and that project was HCC was telling because of the non-metal inclusion, they had a lot of rejection in the forging. So we have done the upstream processing also, downstream also we have worked, and my colleague Devalai Chakraborty also helped me, also helped in this area. So basically here we have defined some forging schedule, that is we identified, because we basically based on the critical experiment, we developed this processing map, and then we have identified the window of that is your state date and temperature for different stages. Okay, so during the basically forging, multipurpose forging, so you can define initial stage what should be your window of temperature and strain date such that you can do the same deformation. So similarly, for different parts, we have defined what should be your window. For example, you can see at low deformation level window is here, that is your high strain date and high temperature. And then as the extent of deformation increases, it moves down here and here, here, here. So that way we have defined a forging schedule. And recently one of my PhD students also done the inclusion modification using the rare earth element.
Just 3 more minutes.
Okay, okay. So rare earth element. So we have also got a core shell inclusion here you can find. And then we have defined one, basically we have defined one model by which we can define why this core shell inclusion, that is the core shell inclusion form. This is based on the simple single core model and considering the aluminum, sulfur and rare earth migration. So the that is the product layer is the aluminum layer. And also we have defined what should be the minimum diameter of the inclusion that can be completely converted to the core shell inclusion, okay, during the soaking period. Basically, it is not that at high temperature operation you get some inclusion and the sulfur completely gets dissolved into that. And during the soaking and the deformation, the inclusion character changes significantly because the sulfide start precipitating and all these things. So all the core shell inclusion basically formed during the soaking period when we allow sufficient time for the diffusion such that the sulfide can precipitate over the inclusion. So this thing, and also we have defined a minimum size of the inclusion, then the starting inclusion which can be completely converted and how much time is required. So we have found that when the diameter of the inclusion of the say 5 micrometer, then it can be completely converted, and if it is more than that, it cannot be converted. Okay, now I will just talk about something about the two areas. I will just skip down just slides. I am not going to details of that thing. So another area I contributed in the welding side, I think significantly because I have visited Big State University a number of times, and we have developed a 3-dimensional framework of fusion welding, and that code have been written completely, and because I had some experience with the TCT code at the time, and we have changed that code and completely in the 3-dimensional framework for fusion welding, and later on this fusion welding code has been applied for fusion star welding, electron welding, and a lot of other people joined that time, so it has been done. So we have defined also different complex shape of the weld pool, and then we have cooling rate and the peak temperature, we have done that thing, and finally we have developed a electron beam welding setup at Pattapu. It was a MOU between the BRNS, GAE and the IIT Pattapu. Professor Goutham was the PI and then Professor Manna was the PI, and when Professor Manna led that, he has given me this task. And finally, we have developed this machine there, and we have done some dissimilar welding. One of the most important results is the copper SS joining, and we found that at high temperature, basically, if you use a beam oscillation, because our machine also has the capacity to oscillate the beam, then you can increase the ductility of the welding significantly, 2 times improvement in the ductility. And what we find is that because of the beam oscillation, there is a charging action, they basically mix up the, basically copper and the steel, copper and steel iron do not have visibility because they form the 2 different phases, but the charging action basically disperse the copper very uniformly, and they also backfill the cracks.
Sorry, conclude.
Okay. Okay, sir, just 1 minute, sir, because this is one of the hypotheses that we have developed, why the charging action basically gives a very uniform distribution of heat mixing and all these things. Because when there is no, when the heat source is moving in a one dimension, you can find basically because of Barui convection, the heat is basically the convection is that is the radially outward. So heat is also moved radially outward, and there basically gives one dimensional heat transfer direction in this direction, and columnar growth take place. Okay, but when you have a that is the beam oscillation, what happens is that in that case the speed also increases, heat input per unit length also increases. So it is not a single whirlpool that is formed. Basically, this is the number of whirlpools that form in sequence, and they have this whirlpool has number of interlocking with them, and heat transfer takes place in each whirlpool by Barui convection. So there is basically a zigzag motion of heat because of this overlapping of the whirlpools. Because of time limitation, we have done then also sponge iron production using Gour furnace. We have done several experiments. We have seen the effect of the, because I do not have time. Okay.
Skip this.
So you can conclude.
Okay, fine. So basically, there also we have seen a lot of heat transfer influences there, and then we try to reduce the heat transfer by optimizing the carbon into the pellets. And we have done a lot of exergy analysis also. Basically, exergy is, as you know, basically this gives the available energy for the stream, unlike into the energy. And also, exergy can include that is the energy degradation in a particular process because of irreversibility, and also it also includes that is the waste stream where the exergy get lost. So exergy destroyed the loss. Like okay. So we have done carbon analysis, and we have found that RHAPA process is also much better than BAPA process also. So from sustainability point of view, and we have also developed a RHAPA alloy steel plant Goutham. This is the basically we have demonstrated because it was a project for Uchchadara Avishkar Yojana, that is the around 7 crore. Okay, so we have finally developed a rotary earth furnace and demonstrated that is the alloy steel plant Goutham, and we have made the sponge iron out of that is the what is the iron bearing solid waste that the carbon put composite there. Okay, this is the acknowledgement because this work cannot be done by myself. Also, a lot of PhD students have helped only this part I discussed, and some colleagues were also involved in this thing and sponsored MHRD and the MES Institute of Steel. So thank you very much.
So today I'll talk about how do we design new materials or optimize existing materials using some computations and machine learning. So just acknowledging the people who actually do the work. So this is my group about 6 months back. We'll update this photo probably next week. And then acknowledging all the funding agencies and the supercomputing resources that we use for our work. So just as a starter, right? So our group broadly works on energy materials, and the motivation or the reason why we work on energy materials is because if you look at technological innovation cycles, so this is basically how much time you actually spend in sort of inventing a technology and then ending up in the market, like commercialization. right? So the blue bars basically show how much time is spent in invention, the yellow bar tells you how much time you spend in deployment. We spend a lot of time developing new technologies, and the innovation is particularly slow in the energy sector, right? Be it energy generation, energy storage, or energy harvesting. And this is where we need rapid identification of new materials or optimization of existing materials, so that we can actually improve the performance of such applications. So with that as our primary motivation, our group works on three major application areas. One is trying to design better electrodes and solid electrolyte materials for batteries. So these could be lithium and chemistries or beyond. Second is to identify better light absorbing semiconductors that can be better than silicon for photovoltaic applications. And third is designing materials that can both generate hydrogen from water using thermochemical means, and also sensing hydrogen at fairly low concentrations, which is relevant for hydrogen storage and transport. So these are the three application areas that we work on. In terms of the types of work, I'd say that also falls into three categories. So we identify new materials for a given application. So that could be, let's say you have a battery, and then we try to identify new electrode materials. We also try to understand underlying materials better. So let's say you already have a candidate and you don't understand some thermodynamic defect, kinetic phenomena that's happening. We try to throw some light on it. And then third is to make ourselves better, make theory better. We are a fully theoretical computational group. So we try to make ourselves better and build very good models. And in terms of the tools that we use, so we use density function theory. That's our workhorse. So we do a lot of these calculations to generate data. We also do significant amount of machine learning. So I will give you examples of the types of machine learning that we do in our group, and we also do a lot of molecular dynamics as well to track kinetic phenomena. So in my talk, I'll sort of give you two examples of our work. So one is how do you use transfer learning approaches. I'll talk about what transfer learning is. And then I'll also give you examples of application-driven research, where we got approached by industries to solve some of their problems, and we helped out in solving their problems. Okay, so the first thing is the idea of transfer learning itself. So to sort of motivate that, right? So if you look at material science, metallurgy as a domain, right? So we are a highly data constrained domain. So what I mean by that is, so let's say you want to track diffusivities of ions in solids, right? We don't have a lot of data on diffusivities. Maybe for few hundreds of compositions or few hundreds of structures, we have some data, right? But it's not thousands, it's not tens of thousands. Same thing for defects. So if you want to understand how to form defects within different structures, we don't have a lot of data. And this also applies or extends to catalysis problems, right? So let's say you are looking at absorption energies, we don't have a lot of systematic data. So material science as a domain is a very data constrained domain, which implies that we cannot straightforwardly take some deep learning architecture, like machine learning architecture, and apply that to materials problems. That just doesn't work. Those models will be overfit, they won't be transferable, right? This is where the sort of idea of transfer learning comes in. So very briefly, in transfer learning, what you do is you use deep learning frameworks, so you use deep models, but then you try to pre-train on larger data that is more available, and then fine-tune it on the smaller target data that you really want the model to do well on. So to give you a vision example, right? So let's say you want to classify images of tumors. So let's say you have 1,000 images of tumors, 500 of them are malignant and 500 of them are benign, right? And you want to classify them. It's impossible to train a neural network model which will do a good job, training on just 1,000 data points. So what you can do is actually download millions of images of cats from the internet. That's readily available. Just one Google search, you can download them. You can train a proper neural network model. Here, the example is a convolutional neural network model. You can train that model properly, right? And this model will be able to predict whether an image is cat or not cat, right? So basically, this model knows how to read images and then put together those images to identify cats, right? Now you transfer most of the learning that this model has done, right, on reading cat images. So we basically, how do we transfer learning? Basically by freezing some of their weights and biases. So machine learning models are a bunch of weights and biases. So we transfer those weights and biases into a newer model, right? And we only retrain or fine tune a small portion of the new model on the limited data that we have. So we basically transfer most of the knowledge that the model already has learned about how to read images, and then we teach that model or fine tune that model to identify tumors very well, right? So this is briefly how transfer learning works, and this idea we can use it within material science as well. So we wanted to sort of answer two questions. So how useful is transfer learning really in material science? We sort of don't know, or no one did a proper benchmarking before. So we wanted to answer that question first, and if it is useful, are there optimal ways to use? And then there are also ways to create what are called generalized models or generalizable models. So these are models that roughly understand structure property correlations, but they are not particularly good at predicting any specific property. But you can take these models and fine tune them very quickly. So you can make these models very good at predicting one specific property very easily. Right? So we wanted to broadly answer these two questions. And the architecture that we used for addressing all of this is basically graph neural networks. I don't have time to go into the details, but I'll be happy to take questions if you have it. Okay, so let's look at some of the results, right? So we looked at how transfer learning, transfer learned models perform compared to models that were trained from scratch. So scratch models are basically you take these neural network models, you train them just on the target data set. Whereas in transfer learning, you pre-train it on one data and then fine tune it on a different data. Right, so I'm showing the performance of models that were trained from scratch on 7 different material properties. So GB stands for shear modulus, this is phonon frequency, formation energy, this is computed band gaps, piezoelectric modulus, dielectric constant and experimental band gap, right? So the abbreviations are all here. And each square has 2 triangles, right? So the lower triangle stands for R2 scores, how correlated the data are, and the upper triangle stands for mean absolute errors, so how quantitatively accurate the data are. You generally want higher R2 scores and low mean absolute errors. All the performance metrics that I'm displaying here are all test scores. So these are all data points that the model hasn't seen during training, right? So these are the performance of models trained from scratch. We can now compare this with transfer learned models, right? So I'm showing a bunch of transfer learned models here, right? Where the y-axis basically represents on which data set the model was actually pre-trained. So the first part of the training. And the x-axis basically tells you which model, which data the model was actually fine-tuned on. So what is it trying to predict? So basically you can compare the performance metrics of all models across each column, right? And the yellow boxes basically tell you which are the best performing models, right? So straight away you can see that all the best performing models are all transfer learned models. So they are always better compared to models that are trained from scratch. There are also other sort of nice takeaway messages. So pairwise models are better than scratch. I'm also quantifying the improvement in R2 scores and mean absolute errors. The best models are for predicting DC properties, so shear modulus, phonon frequency and formation energies, and this has to do with how the data set is actually distributed. There are also other interesting sort of takeaways. So one thing is we don't really have to worry about which property we pre-train on. That really doesn't seem to play a significant role on the performance of the model after fine-tuning, after the second step. And the second important takeaway is there is no real symmetry. So if you think about which model or which data gives you the best fine-tuning performance for a given data set. So let's say you take the example of predicting experimental band gaps. You get the best predictions when you pre-train with shear modulus, right? But for predicting band gaps itself, that's not necessarily true. So if you pre-train with shear modulus, you don't necessarily get the best performance in predicting band gaps. So there's no real symmetry between which data set you have to use for pre-training and which data set gives you the best performance after fine-tuning. Okay, so that's basically answered one half of our question, which is whether transfer learning is useful. The second is how do we create more generalizable models, right? So we took our same graph neural network architecture and we thought, okay, instead of training on one property at a time, if we train on multiple properties at the same time, maybe the model can create better structure property correlations, which is what we did here. So we just modified the what is called the prediction head of the model, and then we tried to teach it multiple properties at the same time and the correlations of those properties with the input structure. And we also tested this model, so we wanted to see how good this model performs, and we see that on a data set that is completely different. So this is band gap of 2D materials. We train the models on or pre-train the models on 3D data. So shear modulus, formation energy, and so on. These are all 3-dimensional properties. So we train band gaps of 2D materials, and we see that our multi-property pre-trained models or M3D models with more generalizable models perform much better compared to simple pairwise transfer learned models. Right? So we also found a way to create better generalizable models. And with these models, we then apply to the problem of predicting battery rate performance. Yeah, 2 minutes, I'll be done. Yeah. So, battery rate performance, so when you think about what sort of governs the rate performance of a given battery, it's basically the diffusivity of ions within a lattice, and these diffusivities are controlled by these migration barriers, which are all material dependent quantities, but you don't have a lot of data to predict these quantities. So we actually compiled a data set. So this data set has about 620 data points, so we manually compiled them. We took our multi-property pre-trained models, the generalizable models that I showed in the previous slide. We had to do some modifications to that model to make sure that the model actually understands directions of diffusion. And once we built these models, we found that our transfer learned models are way better compared to any classical machine learning models, and even the so-called universal machine learning potentials. So these models are way better, and these models also have excellent generalization and classification abilities. So they are able to classify whether a given structure is a good diffuser or a bad diffuser. They are also able to extend learning. So if you train the model only on diffusion of lithium, they are able to start making predictions on magnesium or sodium. Right? So they are also able to generalize to scenarios that they have not come across before. So with that, I have completed transfer learning. So I just give you 2 very short examples of industry-driven problems or application-driven research. The first is where we worked with Shell. So we worked on 2 aspects. So one is designing sensors for hydrogen. So hydrogen, as most of you know, is a colorless, odorless gas, and it's fairly explosive, just like that sound. Right? So we probably need to develop good sensors to make sure that we detect any leaks for hydrogen. And the idea was that we wanted to look at zinc oxide or metal oxides as a class of materials.
Just present the result.
Yes.
Give introduction.
Yes. That's what I mean. Yeah. So what we basically did was we used density function theory-based calculations to look at zinc oxide surfaces and absorption energies, and we predicted that if you optimally decorate zinc oxide with some platinum clusters, these can actually perform very well in terms of sensing hydrogen. And this we also collaborated with an experimental group to verify our results. So this is one example of our work. The second example is on carbon dioxide reduction to methanol. This is a catalysis problem. Here we looked at some 2D materials with defects, with line defects present in them, and these, showing a bunch of data here. If I don't go into the data, I'll waste too much time. Right? So we looked at a bunch of defective 2D materials, and we found these materials to be promising for carbon dioxide reduction. The final example is another project with a company called Scheffler. So they wanted to look at lithium deposition on copper current collectors because this is relevant for solid state batteries. So here we basically wanted to look at the interface forming between lithium and copper, how stable the interface is, what kind of transport you have across this interface. So in order to model that, we actually generated a machine learning interatomic potential. This is a machine learning model that's very good at predicting the properties of lithium copper systems. And we predicted a bunch of properties. Again, won't go into the details in the interest of time. With that, I will conclude my talk. So, density function theory-based calculations along with machine learning can be quite useful for energy applications. Our group works on these 3 topics. I presented examples on transfer learning and also research with industry applications. With that, I thank you all for your attention.
So, good afternoon, everyone. So, I'll just quickly introduce about myself. So, this topic is mostly industry related. So, I did my master's in University of Washington in the aerospace department. So, there I worked with Boeing and US Air Force. So, if you see this aircraft wing, so every time if they want to develop new aircraft wing, they have to do a lot of tests, lot of fatigue tests, lot of static tests. So, but it's very expensive and it's also very time-taking process. So, can we develop computational models that can capture these huge structures, right from like Cooper level to large structures, wind turbine blades or aircraft wings. So this is what we have done. So these are called scaling laws in composites. So this can capture the strength or the residual strength of the structure. If there is any given crack or external impact, it can predict the life of this structure. So later I worked in a launch vehicle startup called Cosmos. So there I led the composite department. I'll just quickly show the video of the launch. Yeah. So if you see the outer structure, these are made with carbon fiber composites. It has to be very lightweight and it has to withstand all the loads, mechanical loads, aerodynamic loads, and the thermal loads. So this we launched last year. So the structure has to optimized in terms of weight. This is very critical in launch vehicle companies because 1 kg of satellite they charge 10 lakh rupees. So if we can reduce the 1 kg of complete structure mass, we can improve the payload capacity. But we need to make sure it has to withstand all kind of loads. Yeah. So we also developed this hydrogen storage tank. So the problem with the hydrogen is it has to be stored in very high pressures. We are talking about pressures of 1500 bar. So in generally the gas cylinders in house it's close to 20 bar, but here it has to store at 1500 bar burst pressure. So this cylinder also we have developed successfully. So we are also part of the Hyperloop team where we achieved first thing is 14 in the world in this competition. So the topic of the presentation is on the prepregs, which we develop prepreg machines. If you see the rocket missiles, the rocket missile, the aircraft structures, anything, they need these raw materials. They need the composites. So we have developed this prepreg machine. So the size of this machine is like 14 meters in length, 12 meters in height, and 5 meters in width. So just to explain the challenges and the technology. So the previous challenge faced in defense, because they need raw material, they need to produce these missile structures. The biggest challenge is, they used to import this raw material previously from Hexel, with a few companies. Per kg, the cost per kg is 20,000 rupees. So what we have done, we have completely designed everything from scratch. We developed this machine. Now, the production cost we brought down to 7,000 rupees per kg. Previously the cost of the machine from the imported machine is like 10 crores. Our machine was like 2 crores. We not only bettered the cost in terms of cost effectiveness, but also the energy consumption of the imported machine. So our machine consumes less energy than that. The biggest challenge is how to remove the solvents in these resins. So that I'll explain in the coming slides. So just to give a brief introduction of this machine, it consists of unwinder station, which it unwinds. Then the initial material will be the fabric. So it unwinds the fabric. Then there is a preheater which removes the moisture in the fabric. Then there is a drag station which pulls the fabric into this impregnation stage. So the drag station has to be designed in such a way that it cannot include the residual stresses in the salt or the fabric. There are heating zones where we remove and heat the resins, and the water cooling station where we cool the prepreg before impregnation. And then the rewinding. So I'll just talk about the heating zones, design of the heating zones. So if you see the other heating systems, they used to use IR heating to heat the resin system and also to remove the solvents. But the problem with the IR, it cannot remove the complete solvents into the resins. So our design, actually we design such a way that it heats the fabric as well as it removes the solvents in the resin. So the other machines which we developed is a torpedo machine. So this can be used to make storage tanks. The previous machine, it can produce the width up to 1 meter. This is like smaller version of this bigger machine. So it can produce width up to 6 mm. So this we can use to make storage tanks or rocket motor casings. Some comparisons with our machine versus imported machine. The imported prepreg. So if you see the Hexel, this is the gold standard in raw materials. So in India we used to import these raw material in tons of tons. So with our machine we were able to achieve actually close to those Hexel properties within 10% of this mechanical properties. Of course there could be, we can do a lot of research on the resin, how it is connecting to the fabrics, etc. So the other applications of the prepreg, so we can use this in launch vehicle structures, PCB laminates. They also use the glass fiber epoxy prepregs, metro coaches. So using this machine, can we develop multifunctional composites? So that is the biggest challenge. If you see the current structure, it could be air taxis, helicopters. They don't have this self-sensing capability. every time after 6 months or 1 year, they need to do the MVD tests to figure out, okay, the structure is safe or not. But can we develop a material that can self-sense its life, like a smartwatch? So this also we are working currently. So this can be used in reusable launch vehicles. They don't have to scrap the material every time or the structures every time. And also in the structural batteries. Yeah, thank you.
So today's talk is focused on the innovation and entrepreneurship aspect. So I'm basically swinging between the two of them in a way, and I'll be focusing on the photovoltaics effort that we have developed in the lab and now almost on the cusp of translating it into the commercial markets as such. So I call it adaptable photovoltaics in the sense that they are adaptable to different structures and different atmospheres. You'll see what I will talk later. So science-driven innovation was one of the main themes here. So essentially, if you look at this image here, what you're looking at is a road, and there is a car down the road, but it's kind of lost in some elusive nature. This is what we call a mirage, and we essentially use this mirage to detect defects in semiconductors. That's the core work that I do here. And this is called photothermal deflection spectroscopy. So we have basically set this up as a capability at IISc, and this is the only one that exists in India, and probably the only one in Asia as well. What it essentially does is it essentially detects defects in semiconductors compared to the typical non-contact, non-invasive methods that exist, which is called UV visible spectroscopy. It's a very simple technique which many people use in laboratory atmospheres. And if you were to have just the material, and if you measure the absorption of, let's say, for non-physicists, it's what colors does a material absorb and how pure is the semiconductor in terms of color absorption. And if you look at UV vis, it essentially has very less sensitivity, so you can observe a semiconductor band gap over here. There's a very small drop in this purple curve. But whereas if you were to measure the same sample, which is nothing but a sample coated on a piece of glass, so there's no device involved here, and you measure the same sample in the PDS, you can see the semiconductor band gap very precisely down to 5 orders of magnitude sensitivity. So this essentially translates to parts per million level of sensitivity. And this sort of complements what Sai is doing on the theoretical front. We actually come from the experimental point of view as such. There are some other advantages to this technique. It's not sensitive to any detectors. It actually has a very simple detector. I couldn't put the cartoon because I had limited time. We can talk later if someone is interested. Essentially, it removes all the optical effects, thereby giving it more sensitivity. So that's what it does. So the mirage part is actually my detection. So I use the mirage as my detector, rather than detecting using a semiconductor as a transmission mode measurement that typically happens in a spectrum. So I'll go a bit further. So what we have done at IISc is built the second version of this tool. The first version was my PhD essentially at Cambridge. So that's the only tool that exists in Europe at the moment. And now that I have come back and I was hired for this tool, we have built the second version that goes beyond measuring semiconductors. And what we essentially do is try to use this for various other fields other than semiconductors. So that essentially involves screening. So this is something which we typically do with this, but we are doing things around biosensing, because one of the key aspects in biosensing is you need sensitivity and selectivity. And the sensitivity part is missing in absorption usually. So people usually go with radiative emission based techniques. So for example, COVID testing was done through RT-PCR, and that was a radiative measurement technique. And most of our detection, the biosensing happens in radiative mode. But with this technique, we actually have sensitivity using absorption, which actually gives us a way of doing marker free sensing altogether. So this is one area of my interest which we are trying to sort of focus on. Moving further, what do we do with this? I'll give you a quick snapshot. So we develop some materials. I'm not a chemist, but we do some material synthesis in our group. And these materials go into testing. Typically, you do different device testing, and then if finally everything works, you develop your product. So this is a usual cycle that you go through. But then there is a loop here where you essentially test your devices. They probably don't work to the level you want, or you discover something that is wrong. You basically end up being in this loop for a long time, and you spend a lot of time and money. So what we essentially are looking at is cost versus time scale. You develop your material and then you go into this testing until you reach the final optimized stage of a product. So what we do here is we come in at this material stage and we essentially test the semiconductors using this technique. So we use it as a rapid testing tool in an experimental sense. And we essentially can predict where these materials can be used in terms of semiconductor applications. There are so many applications that exist in this sphere. And essentially direct the efforts into the right direction, and thereby preventing some of the downstream loss of time and effort that exists. This applies both to research and industrial life as such. So, I'll just give you a brief intro on perovskites because the photovoltaics are based on this semiconductor. So this semiconductor that I am talking about is kind of a crystalline semiconductor, looks like this, generic formula of ABX3, where A is like a monovalent organic cation, B is divalent metal, it could be lead, tin, germanium and so on. We usually use lead in our systems. X is halogen, either iodine, bromine, chlorine and so on. So a typical perovskite which we use as a semiconductor is methyl ammonium lead. The other oxide semiconductor perovskites, the materials which are not semiconductors, which are well known. And again, there are different classes for perovskites. Perovskite is not just one material like silicon. And when we hear semiconductor, we hear silicon, but that is just one material. And you end up doping it to create different variants of it. Here we can actually change these structures and we can achieve different classes of semiconductors just in perovskites. Okay, so you can have something that is conducting in all 3 dimensions, or you can have layered structures which can conduct in just a sheet. So it's a 2D layered structure. And this field is kind of very hot in terms of semiconductor and optoelectronic sensors area. So there's been a lot of work done in this field in photovoltaics, LEDs, sensors, lasers and so on. So there are a lot of different aspects which are fueling this field. So I'm just showing you some LED devices that we make in our group, some of the photovoltaics work which this talk is based on, and there are some other properties which are actually quite attractive compared to silicon as an alternative semiconductor. So one of the key things I will mention here is this semiconductor is solution processed. So you can actually make an ink and actually process that into a thin film using just an ink. So you can use as simple deposition technique as an inkjet printer if you like. So that is as cost effective as compared to silicon, which is a multi-step process, very highly thermal budget important process. So what we have done with this is we have actually translated this to a startup, and the startup is called AVX3 PV. Essentially the semiconductor itself is in the name. And we are one of the first startups which is developing end-to-end technology, starting from the manufacturing tools to the process to the end product. So this is what the entire value chain we are trying to target. And it is an IP-driven startup, and we are like 3 faculty co-founders and 1 industry veteran which is involved in this. So what are we trying to do here is, so essentially you have silicon, which is your existing technology, and this has sort of a long gestation period development, so kind of more than 50 years of development. And the efficiencies we currently obtain is around 23 to 25%. That's how much power we convert from the incoming line. And currently what I'm talking about is hybrid perovskites, which have just been in the development just over a decade. And we already reached the efficiencies of silicon at the moment. And this is completely wafer-free technology. As I said, it's just an ink being converted into a thin film. Now, what else is there? In the silicon world, we essentially import all our wafers. We don't make our own wafers, essentially the single crystal, single junction cells that we make. All the manufacturing tools are imported, so that's one of the dependencies that we have. Other than that, there are 2 other extra things which I would like to mention. Let's say you take a typical panel that you essentially have outside. That panel would weigh anywhere in the range of 25 to 35 kilos. So you need specific infrastructure to hold such a panel. And there is low light performance. So if you have an overcast condition, your performance drops to below 10%. Compared to that, we have completely indigenized manufacturing tools and materials. We can also make our panels lightweight. And they also have very good low light performance. In fact, it exceeds the normal light condition performance. So you can use it for indoor photovoltaics. What are we doing with this is we are creating platforms on rigid glass. We can make them on flexible plastic sheets so they can be very lightweight. We can also combine them with silicon. Instead of competing, we can combine the two and win the race as such. So we can get higher efficiencies. So manufacturing is cheaper. As I said, it's basically manufacturing using it. So if you look at the problem versus opportunities, you essentially have higher weight and heavy rigidity. So per unit watt, you essentially, per unit weight, watt versus weight, you have very low metric here, whereas you can make ultra high lightweight solar cells here. Low core light performance, and these are some of the aspects. So where are we? We essentially work here in the ISC lab scale. We have now scaled up to almost 30 centimeter plus 30 centimeter modules. That's what we do. And we are going into productization using our indigenous tool set that I'm just showing you. So this is all made in Bangalore. Now, just my last slide. So basically, the main focus for this award, what I submitted, was to actually have an adaptable photovoltaic. So if you go to rural India, you essentially find varied household structures, which are not sort of compatible with the typical silicon photovoltaics that you have. They are very heavy, so it's not compatible with this. If you just look at one such program, the PM Surya Ghar Yojana, which essentially envisions putting solar on the rooftops of individual households, you will see that there is higher urban uptake than the rural uptake. And some of this major factor is because of the rural household structures that you essentially have. Okay. And if you just take example of Bangalore, if you take Bangalore urban, you have more than 5,000 installations, but in Bangalore rural, you have hardly touched 400 installations. So this is kind of the discrepancy. So these photovoltaics essentially are trying to address this aspect. And if you look at the rural versus urban capability, the rural actually has more conversion capability in terms of power. So there's a lot of things to tap into. We are trying to target this market, other than space being one of the markets. So my earlier speaker Shiva was talking a bit about that. Like weight is the main metric. So I'll end with this slide. We're making ultra lightweight solar cells. We have quite a few customers who are interested in this tech. We're currently in the stage of setting up a pilot by summer to somewhere after summer this year. And this is Union Minister inaugurating some of the panels that we are making, some of the flexible panels and rigid ones. So I'll leave you with this. Thanks a lot to the team at ISC and the company. Thank you.
Good morning, everybody. I would like to thank Aini for giving opportunity of presenting my work in the translational research under this platform. We are working in the field of early disease detection and functional tissue development. So for this award, we have started with the oral cancer. We all know that oral cancer is a major healthcare burden, and it is not an issue for the global, but it is a major issue for the Indian healthcare burden also. So, but the main problem in the oral cancer detection is that most of these things are detected at the late stage. And if we see, this is the current scenario which impact the 5-year survival rate to the 20 to 30% and huge economic impact. So our desired state is the zero or minimum patient delay, professional delay, and a screening system which should be the non-invasive. Because if we see that at present the detection system is the biopsy based. So when a person develop a kind of lesion inside the mouth, then only they generally visit to clinician, and the only way to see to take a biopsy, which is introducing a kind of wound. So our main aim is that to make a non-invasive screening kind of tool so that it can screen any patient who is just visiting any hospital or pathological center, so that they just give some of the sample in a non-invasive way and it can detect the risk of the oral cancer. So this nature of the innovation is very simple one. We have taken the samples from the exfoliated cells from the buccal region. Then using a microscope, this imaging platform has made under our research team, and this is a kind of multispectral microscope. So another important part is that we don't use any kind of stain to see the cells. So we basically take the cells, make a smear and see under the microscope. So based on the metabolic status of the cells, we get certain features and which give us information whether the cells are at the safe zone or it is moving toward the risky part. So in that way, it is also helpful for detecting the pre-cancerous stage, which is otherwise very much difficult to detect in the normal clinical scenario. So when we are taking this image of this autofluorescence, these images are very feeble because since we are not using any external dye, so we use a AI-based image processing technique, pre-processing technique, and all these things to enhance the image and reduce the noise level. Further, at this system, we integrate this AI-based classification model to discriminate between the normal, suspicious, and the cancer. This suspicious group will fall under the pre-cancer category mostly. So this nature of the innovation is multispectral imaging. We are not believing or we are not only depending on a single type of autofluorescence of the metabolites. We are taking 3-4 signatures of the cellular metabolic status. Then we are interpreting them. This is label-free detection. We are not using any stain here, non-invasive, because we are taking the exfoliated cells, and sometimes saliva is also helpful. And we are integrated the GAN model and cost-effective screening system. So the main purpose of the project is to point at chair screening as well as the chair side screening. This is one of the problems when we actually interview some of the practitioners in the dentistry as well as the head and neck cancer. They sometimes found that when we are taking the biopsy, the result usually comes after 5 to 7 days, and patient has to wait after that time. And sometimes this result is given a high false negativity or the false positivity, which is another burden for the patient, even after waiting that long. So this is the main this is the main thought from which we have started this thing, to make this thing economically feasible, no input dependency or reduce the cost, because there are certain things which are already available in the market like the Velscope and all these things. But the problem is that either they are taking the on-site thing, like inside the mouth, they are just putting the probe, seeing how the cells are changing or tissue are changing. So this is not giving the broad dynamics of the cellular level, or their cost is very high. And no system is available where the imaging platform is integrated with the AI-based decision-making system. So this is the basic system that we have made. This is the multispectral microscope using this different type of autofluorescence sources. We typically use different LEDs for excite the cells at the different level and to see the signature of this thing. So there is one small video which is summarizing the entire process. We have started with this mobile phone camera, which is not that well made, but further we are just using, this is actually prostate tissue. We have started with status, and the classification system will appear as an integrated part of the system. So other than that, our lab is also focusing on the development of regenerative tissue formation, and this is basically focused on the deep tissue injuries. So deep tissue injury, this is a kind of problem like from the burn wound, diabetic wound or any kind of wound. This kind of deep tissue injuries happen. The main problem with this deep tissue injury is that the deeper level of the skin get destroyed and our blood vessels generally get destroyed. So nowadays, whatever the system that is available commercially, it is basically covering up the wound and not providing any kind of vasculature structure which can provide the nutrition and further help the growth. So we basically make a kind of multi-layered structure and using different type of stem cells and exosome putting inside it, and we also see if the stem cell can itself convert it to the skin cell without giving any kind of growth factor. So this is the convergent technology using the 3D printing and exosome therapy, and the vascularization to put the different layer of the vascular structure, different layer of the skin along with the vascular structure retained inside it. So this is basically a kind of CAD model. Then we have started doing this 3D printing. After that, a perfusable system has been developed, because when tissue we are putting inside the body, there is a kind of perfusion system. So we are trying to develop a kind of lab on a chip model, though this is very preliminary model, it has been shown here. We are just modifying it further. And the Y channel is actually showing the formation of the blood vessels, because this is the expression of the vascular endothelial growth factor, which is an important factor for the blood vessel formation. So these are the some images which are time-lapse images which are taken at different time point to see how this normal stem cell, without giving any growth factor, only changing the environment, it is converted to the endothelial cells or something. Then we are focusing on the exosome. So we are using exosome as a ink for the bioprinting technology. So exosome is not a very kind of established method right now for the clinical application, but in research it is for the last few decades. So it is a basically kind of generated from the cell by the exogenous process, and it is contain a different type of growth factor, DNA, RNA inside it, and it is actually helping to make cellular communication beside it. So our main purpose is that when we are using the stem cell, we are using the exosome as the communicating element to make the connection between the cells, so that it can give a kind of instruction to convert into the endothelial cells or like that. So these are certain markers which are mostly related to the blood vessels formation. One is the vascular endothelial growth factor A and VEGF receptor 1. It is basically showing when you are trying with the different composition with exosome, without exosome, with 2 or 3 level of culture along with the exosome. So it actually shows that with exosome, the communication of the cellular, the network of the vasculature is forming in much more robust way if we compare otherwise. Then exosome can also be used as a early cancer marker. This is also we are going to incorporate with the prototype that we have developed, because that time we have taken only the cells from the buccal region, but right now we are trying to collect the saliva of the patient. Even if we collect the saliva, we even don't have to put any kind of pressure in the buccal region, because when some patient who are the precancer, who have the precancer lesion, we are collecting the cells from this portion, it is actually bleeding. So we are trying to take the saliva and isolate the exosome from it to make a kind of model if the exosome give a early cancer marker. So we have done different type of biophysical characterization of this exosome. This is the RIR data. This is basically showing how water molecules are interacting with the exosomes of the different type of cell categories. We have taken 3 cells. One is the stem cell, mesenchymal stem cell. Then another is the cancer stem cell, and another is the differentiated cancer cell, that is the HG2. Yes, I am just finishing. So this is basically showing the hydrophilic and hydrophobic interaction or nature of this exosome, as well as their enthalpy and entropy based on this FARIR data. Then we have also done this Raman confocal imaging, which is basically showing or confirming this notion that there are some groups, that carbonyl group, CH group, all these things are present, and which are actually changing from normal stem cell to differentiated cancer cells, and it can be a very positive marker for the detection of early cancer signature. Another work is working on development of the hair follicles. This is for the functional skin generation. After formation of this vascularized part, we are now trying to make a hair follicle so that our skin tissue that we are forming can be the full thickness and fully functional. And for that, we are making different type of organoids out of the different type of cells. So these are some confocal images, and we have taken 3 different type of cells and making the organoids and different days of culture, 7 days, 14 days, 3 days, and we have seen how these organoids are interacting with themselves, and if a necrotic core is forming or not, if the nutrition is going inside or not. Right now we are trying to differentiate these cells to the hair shaft or the hair-like structure. Basically this ball of cells will be incorporated into the 3D printed scaffold so that they can make the interaction and they can make this kind of hair shaft inside this graph. So we have some R&D fundings from Coal India and this PAIR project, Ministry of Ayush and BIDAC, and all this INR, ICMR, all this funding are helping us to achieve this thing. And we are also trying to translate our technology. Since we have just started our incubation, now we are trying to collaborate with some incubators and the companies to make a kind of technology transfer program. And also with the different medical colleges, and the AIMS daily just give us a nod for the pilot study of this microscope, multispectral microscope that we have recently developed. And this is our group. Thank you very much.
So today, what I have promised to talk about the development of emerging magnetic materials and their possible device applications. And this is the subject area which I have been pursuing along with students and colleagues in BRC. Of course, though recently I have moved as director of this another DE-aided organization in Mumbai, and I am still JC Bose Fellow at BRC. Yeah. So, some problem. This is moving, that is not moving. Okay. Yeah, this is moving, but that is not moving. So, some issue is there. Okay. Now, yeah, fine. So, I will start with, in my talk, the proposal is that I will be talking about several magnetic effects, magnetic phenomena, which we have encountered over a few decades. And I will be trying to give you some glimpse of that. And I will also, first I will give very briefly what is the physics behind that, and then what is the technological implications and how much we have done in this regard. So there are certain phenomena I will be talking about, like magnetization reversal, then magnetic exchange bias, then magnetic actuation based on superparamagnets, magnetocaloric effect or magnetic cooling, the spin quantum entanglement, and this is one of the latest subtopics which we have been working on, and optospinodynamics, and then spin-Seebeck effect. So first let me give an overview of this phenomenon, what is called the magnetization when it goes to negative. See, as you all know, magnetization by definition, it is the projection of magnetic moment along the magnetic field vector, but in certain cases I will show you, is though there is no superconductivity in real magnetic material such as ferromagnet, the magnetization can be negative, and we have written this review article in physics reports, and that is what is the citation, and that is supported by our many original papers and many more. And this is the very first experimental viewpoint of this magnetic phenomenon, which we have seen in several classes of magnetic material, right from spinel, garnet, perovskites, and so on. So what is this? As you all know, when you do the DC magnetization measurement from the paramagnetic state, when it goes to magnetic to order state, magnetization increases when you pull this specimen, and in this case it goes to maximum. So instead of getting saturated, it is decreasing, going to zero and going to the negative side. So this is what is the new phenomenon in terms of negative magnetization or magnetization reversal or pole reversal of magnetization, which we are talking about. And concurrently, another magnetic phenomenon which is known as magnetic exchange bias due to interface phenomena, that also shows the polarity reversal. And this we have understood by doing detailed neutron scattering study, which facilities, in fact, this is the very first one I developed after joining Bhabha Atomic Research Center from the training school. And what we have understood at this temperature, what is happening, this is the neutron beam polarization. So you pass the polarized neutron through this sample in the parametric state, since there are no domains, no change of polarization. As soon as magnetization develops, polarization decreases. When the magnetization maximum, you get maximum depolarization. Then it recovers and goes to the same value. That means this is the point, so-called the compensation point, where we have understood the magnetic domain loses its total moment. So domain magnetization zero. By the way, by doing neutron diffraction, we see the internal moments are there. There is a just cancellation, like exact like ferromagnetic material, but here you can say it is just antiferromagnetic kind of. And what is the implication of that? This kind of two states of magnetization state 1 and magnetization 0, that is the two poles of magnetization we are able to get out of these materials, and this is the application in magnetic memory, as you all know, which you have established there. And as I said, there is another concurrent phenomena called magnetic interface effect, that is called exchange bias. There also we wrote this review article based on many fundamental papers, which at present cited this many. And when this magnetization reversal is there, magnetic exchange bias also can change the sign. An implication that we have seen in this kind of even nanoparticle, not only bulk, implication of that, this phenomenon we can use to make this thermally assisted magnetic random access memory. Due to time limitation, I will not go into details of that. This is what we have established. Now I go to another kind of applications of magnetic nanoparticle rather here, the magnetic actuation. So we have worked very closely on different kinds of nanoparticle system. This is for the gamma Ep2O3, nothing but the Ep3O4 with the vacancy at the octahedral side, and this is the superparametric behavior. But at room temperature, each nanoparticle of 10 nanometer diameter typically, it carries huge magnetic moment, 28,000 Bohr magneton, and that is a huge, and this kind of nanoparticle we have used to make the magnetic membrane. And based on this magnetic membrane, what I will be showing, the artificial heart pump support system we have established in collaboration with the cardiac surgeon from the Fortis Hospital of Chennai, and 3 patents we have got, and so on. So this is the principle that this, as you know, when the heart fails totally, there is at present the pneumatic means it is there, but so there what happens, the helium cylinder is connected and helium gas actually used, and this cable passes through the chest, and the patient dies because of the infection, because cannot take bath, cannot go home, and so on. So this is one the prototype displacement pump which we have established that can be used by magnetic means to sort out this problem that there is no cable goes through because magnetic field can penetrate. So this is, and this can have many other applications. Now I quickly move on to the very recent topic, that is the quantum magnets, and this is in tune with the National Quantum Mission, as you know. But we have been working in this area over several decades. In fact, beyond that, right from 2006. We have been working, I am showing, but this is one typical quantum phase diagram. I will not go into that. Rather, I will speak about another compound. In this case, we have shown that the qubit, which is represented by this kind of spin entangled state out of the electronic spin, how we are getting the entangled state, and this spin entangled state we are able to demonstrate in several compounds, which is extremely rare and the very first of its kind, that this entangled state of spin entangled state exists even at room temperature 300 K, which is unbelievable. The first paper we have published here and the second paper under consideration, and this is what is the entangled state, and this is the quantum one-third magnetization plateau, which is nothing but the macroscopic evidence of this quantum entangled state at this elevated temperature, which you all know that quantum entanglement due to spin, it is feasible only about milli K or so, but this is what is demonstrated there. And what is the technological implication? That means if I use this material and make the qubits, my qubit will be there, that property even at room temperature. So this is what can be, this kind of material eventually can be used for making the quantum computer, which will be working at room temperature, because you need these quantum qubits out of spins. Of course, technological front in aligned with the quantum mission, these are the work we have made this kind of cavities, because once you make the qubit, how to interact? So you have to make the superconducting cavity inside this qubit goes, and then interaction goes by electromagnetic means, because spin you can interact by electromagnetic means, and then at low temperature you have to test this interaction, and this is the way. So also there has to be control system to control it. So this kind of activity we have been doing, and so because of time limitation, now I go to yet another magnetic effect, which is known as the high magnetic electric material, where you see the magnetic cooling due to entropy change, which can be used for magnetic refrigeration. We have worked on several compounds, particularly the rare earth-based compounds, and for example, here it is rare earth is there, it is hidden here, and this kind of entropy change is there, which can be tuned by changing composition, and you can tune this magnetic phase transition and corresponding change of magnetic entropy by this compositional means, and this is the relative cooling power, and so on. Now, we have made the device based on this principle, which is nothing but the magnetic refrigerator, and this is the view graph of that. And what I show here, the magnetic cooling, as you see, this is what is my magnet, and this is the rotating device, and this is inside. We have this magnetic electric material, which you have made like a thick film, and when it comes out of the magnetic field, then the cooling takes place, and this is the temperature drop. As you can see, this is from the videograph. So, like that, we have tested several magnetic electric field material and tested their real properties in laboratory. And yet another example, when this magnetic entropy change is there in certain materials. For example, we have worked very closely on this molecule-based magnetic material. Where there can be a situation that minus delta Sm can be positive as well as negative. This is yet another twist of this effect, that both positive and negative we get in the same material. And I will demonstrate in my next program that this effect can be used to make a constant temperature bath at this temperature, because as you know, this part will correspond to magnetic cooling and this part of this card will correspond to heating. So self-sustained temperature bath can be maintained. Suppose you start with your desired temperature should be at the same temperature, while that is polarity change is there. Now let us say to start with, my temperature bath at this higher temperature, let us say 15K, it will drag to this temperature because magnetic cooling. And suppose to start with, it goes due to temperature fluctuation goes to the other side, then it will heat it up. So as a result, it will eventually give you the constant temperature bath if you use that material. So this is yet another application. Now this is one of our latest work. We are working on the optospintonics. So here two ideas we have put together, and this is the patent we have got, rather applied. And two ideas. One is that spintonics you all know. At the same time, you also know the optical detector. And now, how to put these two together? That is what we have done in this work. And here you see the dark current means when you don't pass the, don't put any light, and when you put the light, so the ratio it shows up to 40%. This ratio is very good when you shine this kind of laser light or don't shine. So is the difference. And at the same time, the IV characteristics under magnetic field also you see the change. So this is the magnetic effect. You see the DC magnetization study. This is what you see the magnetoresistance, electrical resistance under magnetic field. So all these signature is said that magnetic and the optical, they are intertwined and they are happening at the same time. Here you see the magnetoresistance when the light is off or light is on. So that means the optical and magnetic there. So this is the new area and we are going now very strongly in this direction. Yeah, I will finish. So this is yet another, you all know the Shiva effect, but here the device which you have, the facility which you have developed is called the spin Shiva effect. You can measure the Shiva effect out of this spin. So when you maintain the temperature gradient, either delta T of different values, and you measure the spin Hall effect. That is what in-house developed facility, and this is what we have measured on this platinum deposit, yttrium ion garnet deposited on platinum, and you see beautiful results. Now, little bit on non-magnetic, because we have done some work. We have this imaging facility. We have developed at the Dhuba Research Reactor, and we have that. This is what we signed with the Director of Archaeological and Museum of Government of Maharashtra, and there all this stuff we can see what is there inside, because Newton can see their variation density and this kind of images we have got. We have also this sodium iodide based detector we developed in BRC, and those detectors are used in a backpack in the compact device. In fact, in G20 summit, all these detectors were used to get a survey without telling others that whether any kind of radioactive material was present during our G20 summit. So this is the direct application, and we did this work in 2022-23, handed over the detectors and made it. We also got recently this patent. We had these neutron detectors based on scintillating crystal. We built where we can measure neutron, gamma, and discrimination is very much possible. And we have been developing the various kinds of neutron detectors. These are called position sensitive one-dimensional neutron detectors. This is the gas filling of helium-3 or boron, and this is the control system, all in-house activities over there. This is same way the two-dimensional neutron detector that was for one-dimensional. This also we are almost finishing this 2D detector. And all these things, many things are possible because these are the neutron instrument which I could develop with my colleagues over the years, and while temperature, magnetic field, all these facilities, these are basically neutron experiments. So with this, I must thank my main collaborator because a lot of work, as you can imagine, many collaborators, but my close collaborators and students, Amit Kumar, Anup Bera, Anil Garg, Deepak Garg, Anil Jain, and this Pooja De and Saraswati Sen. This is the theoretical work, Manoj Kumar from Asian Bose, Dr. K. Balakrishnan from Kochi Hospital, little neutron work we did in UK. Thank you so much.
So presently I am from IIT Gandhinagar, and I got Tata Innovation Fellowship, and I really am grateful to IME for giving me this opportunity, this podium to speak, and for selecting me as the Fellow of Indian National Academy of Engineering. I am from Electrical Engineering and coordinating the Center for Biomedical Engineering at IIT Gandhinagar. So, so before I tell, let me go to my topic. It's freezing of gate and effective solution in smart wear. So freezing of gate, Parkinson, these two terms echo when we tell about freezing of gate. I'll skip this portion about me. So the freezing of gait is a phenomenon where Parkinson patients at advanced stages have the effect of, as a feeling, the feet being stuck to the ground. And so the body moves, but the feet doesn't move, the person falls. So the secondary effect of fall is more problematic because of freezing, the person's fall, it can be hospitalization or even sometimes very fatal. And we can, in fact, this is characterized, which is very visible at advanced stages. There is shuffling of gait, slow shuffling of gaits, which can be an indicator of the person is about to freeze. Now, about 2 lakh cases per year has been reported for people suffering from Parkinson's disease, and they have been reported to use various types of technology, maybe a smart cane or other devices. I'll come to that soon. And prevalence rate shows that since ours is an elderly population, we are going towards an aged population. People above 65 years of age have a tendency of demonstrating freezing of gait and suffering from Parkinson's. This is not all, but there is prevalence is showing that, and so the problem is really starting. It is not only globally but also in India. So what are the solutions? So currently, the doctors use 3 types of external cues, either like a visual line in the form of lines on the floor, which is not a very solution which you can take it out in the field, or it can be small claps, right, or a metronome given to the patient, or to bring out the patient out of freezing condition, or it can be a pat on the back that, hey, you have frozen, please come out. So that are giving external cues, and these cues sort of trigger different regions of the brain so as to facilitate the person to come out of freezing. So every time when I'm telling that out of freezing, that means the person has already frozen, and these are measures to bring them out. And the other is the pharmacotherapy, which is a dopaminergic therapy, which works well, but there are certain issues. For example, in advanced stages of the disease, the person becomes immune to the pharmacotherapy treatment, and the freezing still kicks in. And the present techniques which physical therapists use are mostly observation-based, not quantitative, and it's a lot depends on the individual expertise of the therapist to understand whether the person is freezing or not and give cue. And the other things, when the technology-assisted cues like smart canes, they continuously give cues. The problem is little bit, it still exists. So particularly the continuous cueing in literature have been shown that it leads to cognitive load, which leads to habituation effect, and because of the cognitive load, again the freezing happens. So it's not a permanent solution, right? So what is the way out? We have come up with a wearable solution, which is a pair of insoles which can quantify one's gait. The idea is that there are very nice gait rides pressure mat where it has 3,60,000 sensors impregnated in the pressure mat, and a person can walk on it and you can quantify gait. But you cannot take the pressure mat everywhere. So how we would put the pressure mat into the shoe, and that was the idea which we started with. But at the same time, I did not want so many sensors to be put inside the shoe, because then it won't be a feasible solution. Right. So picking up a gait profile or pressure profile from cardinal points below one's foot is something which we wanted to quantify gait and slide the insole into the shoe, any shoe, and then this gait quantification sort of wirelessly communicates with the central microcontroller enabled device, which is on the belt, or it can be inside a pocket, and which can take a decision whether to trigger or not trigger based on only when the person needs it. That was the novelty which we have already obtained the patent. So it will trigger 3 different types of cues, either an auditory cue or a visual line in front, like a laser line in the front, or a tactile cue, which also we established after a lot of research what will be the optimal location for giving the tactile cue, like small synchronous motors like a buzzer of a cell phone. This is how we extract the gait. In fact, we get from different regions of the feet the real-time measure of the pressure profile, and we can get measures on step time, stride time, cadence, percentage stance, percentage swing, single limb support time, double limb support time. So many 14 to 15 different gait parameters, as if it's like a gait quantifier in real time. And that we felt that, okay, how good are we in getting these parameters? We could see that we have a very high correlation with almost very negligible error with the standard state-of-the-art camera-based systems and the pressure mat system. So we're happy with it. Now going forward, we felt that while a person freezes, the posture also changes. So the bending of the knee, bending of the pelvis takes place. So can we start working from the bending of the knee, right? And we added some knee flexion to it along with our instrumented insoles, and we were interested to look at double limb support time. That is where the person is hesitant of picking up the leg because the person can fall, and which is when both feet are in contact with the ground, that is double limb support time. Or it can be, say, a step time, that is the time taken between 2 consecutive heel strides of contralateral legs. Right. So these are very good indicators of one's freezing of gait. So we wanted to pick up all of these 3 indices, and we did a study where the individual was walking on a straight path and a pathway with a 180-degree turn. The idea was that when the person, particularly a Parkinson patient, turns, there is a chance of freezing. So we were trying to simulate that and see how our system works. We went to community centers and recruited patients in close collaboration with hospitals and clinicians. The individuals will need to do different types of tasks, either walking single task or walking while speaking, like dual tasks, which have been shown in literature to be quite challenging for these individuals. And we used a good participant pool, healthy and stroke. I'll come to the results. So there is a very good indicator that if the person is about to freeze, then we can pick up that from the variability in one's gait. So as if I'm walking, but then I'm slowing down. I'm walking, then I'm slowing down. So if we can pick up the variability in the gait, step-to-step variability, that can be a very good indicator. We can see it's hardly 4 to 5% for individuals, for healthy individuals. Quite expected that the variation will be very less. But among these three, we could find out that even for healthy elderly, about 5%. So for the dual task and the pathway with a 180-degree turn, we could see some variability. That was not a stark difference, given that they are healthy and it will not lead to freezing of gait. What about those with Parkinson's? So we can see that for Parkinson's, so a very interesting story. So Parkinson's, we could see that particularly the step time variability with statistical variations we could find out, and it was very prominent for the dual task and the pathway with the 180-degree turn, and also we could see some promise in the double limb support time and the knee flexion as expected, but we could see that the step time was coming very prominent, right, and all statistical, right. Then we could understand that, okay, but we were not happy. We wanted to see that the current literature or current technologies tell whenever the person is frozen, let me bring out the person from freezing of gait. So what's novelty in our work? Can we predict possibility of freezing? If we can sense variability in one's gait, then we can predict freezing, and then we can take some steps so as to prevent the person from freezing at all. So that was our idea. And so we were trying to find out the pre-fog window, and which is the novel part. We could see that. So we were trying to take instances, say, at the freezing, 1 step before freezing, 2 steps before freezing, and 3 steps before freezing. Because it was short pathway, we could have gone more. But we started with 3 steps before freezing. And we could see for the Parkinson group, with the variability in the knee flexion, correct, the knee flexion, we could see that we could get a pre-fog sensitive window 2 steps before the freezing window. That means before 2 steps the actual freezing kicks in, we are able to sense the possibility of freezing of gait. We wanted to see what about other parameters. For example, in the case of double limb support time, we could see that at least 1 step before the freezing, only 1 step before the freezing, we could catch the possibility of freezing of gait, and that too in a 180-degree pathway and dual task condition. So we thought, okay, what about step time? For step time, we could see a very interesting result. It was able to catch the possibility of one's freezing 3 steps before. So that means we get a bigger window, right? We can sense the possibility of freezing. So we thought that, okay, the step time is coming out very well, but is it a clinical measure? Why will the doctors take it? So we have to prove that whether it is clinical or not. So we chose H&Y scale, which is a very good indicator, proven measure, clinical measure for freezing of one's gait. And we could see that even 3 steps before the actual freezing happens, the step time had a high correlation with the clinical measure H&Y scale. With this, we could very certainly say that it can be giving us a very clinically relevant and quantified metric where I can judge possibility of a person to freeze 3 steps before the person has frozen. So I can get an enough window to give intervention. So now on intervention, we felt that, okay, we know that with different types of cues, the person can be given, can be brought out of freezing. How about giving the cue 3 steps, starting from 3 steps before the person has actually frozen, and seeing the effect, whether I can reduce the possibility of freezing, because that was our final idea. But we wanted to see, we wanted to prove, because if we go to a doctor, the doctor will say, we have a laser cane, what's the great about your product? So we felt that, okay, let us compare with the currently existing continuous queuing versus our queuing. It is as if the person is not feeling well, start the medication. Or the person has a fever, he has a fever, give him medication. And then the person is fine, don't give medication. If needed, only give a medication. So assist as needed. So that was our idea. So we wanted to check ours. And I'll go. Yes, I'll go first. So we combined with the entire queuing system. This was a queuing system where we wanted to compare against no queuing, continuous queuing, and our assistance needed queuing. And this was the study, which I'll skip. So these are the results. So we could see for healthy people, irrespective of no queuing, continuous queuing, assisted queuing, no variation as expected, because they are healthy people. But in the PD, we could see that a lot of statistical variation or statistical reduction in the variability of step time in the case of Parkinson's disease. That is, even in the case of Parkinson, we are able to combat in our assistance needed mode, statistically reducing the variability compared to continuous queuing, the existing model. So we were very happy with that. And then we felt, okay, our algorithm is working on step time. Maybe that's why the step time is coming good. How about seeing other gate parameters? So we wanted to see the double limb support time and the speed of walk. And we could see, so in literature, they say that whenever the person is freezing, the walk speed reduces and the double limb support time increases because the person has to stabilize. We could see the opposite. With our setup, we could see there's an increase in the speed of walk and there's a statistical reduction in the double limb support time. So really we were able to help the participant not freeze at all by taking an action 3 steps before their actual freezing. We could get very healthy feedback, and I think so I can show you a small video to show you. I'll not show with the no queuing. See the continuous queuing. The person is walking, frozen, frozen, it's coming out, right? And without queue, the situation was worse. Now see our assistance needed queuing. So to prevent start hesitation, we give a queue. The person starts walking, little to no freezing at all. So we could see a very good change. So I fully acknowledge the beautiful support of my various PhD students who are around the world now, and even faculty at many of the IITs and outside in India, and my postdocs, my current PhD students. I fully acknowledge the funding support of various national and international funding agencies. Thank you.
Good afternoon, Honorable Chairperson, my friend. I'm going to talk interdisciplinary. That's what we are doing for the past 3 decades and for the past 8 years, the most important directly relevant to the healthcare system. This is about my agenda. However, at a glance are contents of my presentation in 3D way. First one is disease forecasting and climate change. On 2-3 diseases we have taken up. And second thing is a drug discovery and affordable technologies, what we have practically implemented. And the last one is the creation of facility. Creating facility is not an issue. How to make use of it for the societal application, especially in the health sector, is our main concern. So what are the supercomputing facilities of our own? Param 10,000, Param Padma, then now Param Bioembryo. This is my total history of the usage of the Param for public health. And the National Center for the Pharmacoengineering, which is the first one in Asia after North Carolina University in USA. This is the first institute in Southeast Asia to have what is the pharmacoengineering. I will let you know what it is. Then when it comes to the climate change, let me come to the part 8, climate change and its impact on the, let me take one dreaded disease is malaria. This is the CSR program actually started some 15 years back, and they have constructed this kind of 30 meters of the climate, this towers, meteorological towers at a 10 level, 10 meters, 20 meters, 30 meters. And we are going to have one kind of a correlation between the wind speed versus the vector. So that how vector will be promoted by the wind speed, so that wind speed, if it is a passive way, how many villages are covered from one to another, so that those people will be affected by this vector. That is the thing. So we wanted to develop a climate model for that. And this is the model how it will work out, how data transmission will take place. This is a simple one. Schematic, telemetric reception and quality control. See, data generation is not the one. Quality data is important, otherwise it leads to GIGO, garbage in, garbage out. That's why we are particular about the quality data. This is rainfall versus the malaria situation. Then we have developed the, see, but you see the 3-4 decades history, if you see, the impact is so much improving because of the parasitic index in the body which is not getting eliminated. That is most important. So rainfall versus 2003 data we are showing. Again wind speed. Which is the one finally it is showing? Wind speed and rainfall and relative humidity, 3 factors are showing wonderful impact. You see in 2000, in this particular, how significant it is showing impact on the malaria transmission. This our model shows in a climatic model like this. How this model will work? Steps, cases, vector population, calculate the density, and cases that exposure and transmission of this one, simulate the model, compare with the ground model. Any forecasting model exceeds its accuracy 60%, means you take it granted directly, it's a validate. If you get a 70% accuracy, 10% put it in the pocket. Now, this is applicable not only for the vector density, even to the equipment failure, chemical accidents, or aircraft crash. Anything. This is a standard principle. Using this data of the 4 years when we have done it, we got 85 to 90% accuracy of the forecasting in Arunachal Pradesh. It is happy to share. It is being currently used by the government of Arunachal Pradesh for forecasting the malaria. Next one, this is about the Arunachal Pradesh visualizing. After collection of the data, we wanted to put it on the visualization. If any health secretary comes who is not belongs to science, he will go to the red zones and then ask the authorities to control the, arrest the transmitter. That is the one. So that but at least 1 or 2% of the population can be protected from this model. That itself is a great contribution. Let us talk about other non-fatal disease. People will never die, but more than death actually. 625 crores of rupees of annual loss is there in India because of these dreaded diseases. And what we have done for this? Initially, we develop a database, then we do the relational database and develop a model by using the data mining. We have lots of data in India for health. We have little information about it, but we have no knowledge to represent. Then what is the ultimate solution? Data mining. Then we have got the several tools which are available. We are not interested being a health authorities or public health scientists. We are interested only in the application of the algorithm rather than the invention of the algorithm. We have taken the self-organizing map, which is a clustering mechanism for this deal. We have taken the 45 villages as data because in India, with the available facility, with the available funding, it is very difficult. We have got more than 6 lakh villages. You go to that particular village, I cannot be in a position to tell, go to particular state and do the XYZ parameters. Whereas this beautiful tool is able to tell 45 villages of the data is clustered into 3x3 grid system. And I will explain by taking this particular grid and exposing my next slide, you can see the beauty. You see first the one whatever I have extracted. This axis has got the parameters. This is about the parasitic percentage. This is about the vector percentage, infection, infectivity. Let us concentrate on 4. You see the y-axis villages. In this particular village, this particular vector density is more than anything else. In such case, what you do? Go to that particular village, do the vector control rather than drug distribution. That means you are prioritizing at the village level by using this self-organizing map algorithm and go to other side of the coin, opposite direction. These last 3 villages are highly endemic for the infection. That means don't do vector control, go to that particular village. On an average, Indian village population is 5,000. Tablets of diethylcarbamazine is 3 times per day. 3 into 5 days, if you do 15 tablets. 15 tablets into 5,000 population. Nothing, 30% of tablet. So you are actually eliminating the parasite from this for 3 villages. That is a realistic application of control. It is a supplement, not a replacement, let me tell you. So next one, take the data again, put it on the visualization system. Wherever the dark red is there, go and do that one on warp-fit basis. Then transmission will be arrested. If transmission is arrested, if parasite is not there in the body, what vector will come and bite except creating some nuisance by taking 20 cubic millimeters of the blood from your body? So now let us talk another last disease of the first sector in my presentation. Japanese encephalitis, mostly prevalent in Uttar Pradesh, and asymmetric paralysis. Below 16 years, kids will be affected very badly. 15 days if you don't take action, patient will die. 15 days incubation period. That's why in the morning science talk that I asked our gentleman, Ashutosh Sharma, how to reduce the technological incubation period, invention to implementation. So this is the one Japanese encephalitis we have taken, and this is my model how it will work. Let me not explain each and everything, but the title of this algorithm is good old one Bayesian's network. Everyone knows about Bayesian's network in computer language. Bayesian's network is extensively used for the health sector, not in health very limited, and insurance and banking sectors it is widely used. Interdependency of the parameters is the main heart of the Bayesian's network. How I have used it for the first time in vector-borne diseases. This is the one. These are all called dependent variables on each and everything. The one which is showing that arrow here is depending on the other parameters from where that arrow is getting generated. So this interdisciplinary is the interdependency is there. Finally, vector density is depending on one or other. So what you can do, how to reduce that, how to cut this dependency so that the transmission can be arrested. So what is my final program says? A simple application. This is a welcome screen, or you can put that data and you give the output will be appeared like this. Whether this output is correct or not, you can get it checked. There is one more window that is called wetting window. So cross-checking is also there in the Japanese encephalitis. Even now, unfortunately, alternate to year. It is not a pen year. Alternate to year, government of in Uttar Pradesh, Gorakhpur, still people here, students are dying. That is most unfortunate. You can see some 15 or 16 years back, 1,600 children are died because of the Japanese encephalitis outbreak. That is a, if you don't take action, within 15 days, patient will die. Most now, health sector of the vector-borne disease application is over. Let me come to the part B. That is a drug discovery by affordable technologies. I want your attention now because what we are daily facing, how it can be overcome. See, this is the 3D printing. Government of India, Department of Science and Technology, 7 years back, awarded with a lot of competition, with a lot of iterations. National Center for Pharmacoengineering. This is a classic example for that. Biology, pharmacology, mechanical engineering and pharmacogenomics interdisciplinary science. This is a classic example. For example, what it will do, we are doing the 3D printing and 4D printing, and we are doing the next generation personalized medicine. When you go to doctor, he will give you paracetamol 1 week, 3 times per day to you. What is your BMI, what body mass index, what is your pharmacogenomics of your body? Whether you may require only 300, you are pumping unnecessarily 200 extra material to a system, and he may require 700, he is again under given that another 200 there. So in order to give the personalized medicine with a single dose, which is required to the person particularly, this 3D printing and personalized medicine is going to play a major role in another coming 30 years of the public health of India. So this is the one, and I will tell you that directly products what we made by 3D printing. For example, you take this Ghost tablets. It has got the one kind of a, the beauty of this particular thing is stability and safety. There will not be any waste material like other traditional tablets in this particular one. Only single dose, which is you can put 20-30 drugs also into your single dose. And as and when required, your body only dose will be released. Let me tell you about this particular bi-layered 3D printed tablets. There are 2 layers. First layer, one drug will be there. Second layer, another drug will be there. So first layer, once drug will be released, when once you consume the drug, it will go to the stomach first. It will be released at that. When it get absorbed by the stomach, then the second one will come to the picture. What is that one? intestine, that will be released later. No drug-drug interaction here, unlike you may take thyroid in the morning and later on the antidiabetic tablets, then metformin followed by something else, and there is a huge drug-drug interaction, wastage of unnecessary materials pumping into the body, which is not there here. You can also see with this QR chip by taking this, what is the drug and when it is being, what is the batch at all. That means safety of the drug also can be seen here. This is the beauty of this one. This is not only for health, even cartridges also 3D printed, we have done it for the purification of the water. Because India is suffering with the main problem of the arsenic contamination, especially in the eastern parts of India. Now let me see, this is a 3D printed mask we have handed over to the government of Assam and Meghalaya during COVID period. This is the Chief Minister of Assam, he is the governor and all. Now next one come to there is AMTZ, Andhra Pradesh Medical Technology Zone, which is a wonderful medical technology institute is established in Visakhapatnam, and where they have sponsored our programs in a multiple way, and we have given our technologies also to AMTZ for its wider propagation and for wider application. Our know-how is also transferred in 3. I'm very happy to show you, this is a DST Center of Excellence has yielded 6 patents. Out of that, 3 patents have been taken by very good companies for its subsequent commercialization. What is the challenge in the pharmacoengineering here is expensive infrastructure establishment, and it will take its own time for coming to the public.
We have 2 more minutes.
Yes. Now this is about the medical devices. We have got the pacemaker, ECG, and all related to the health related equipments, biosensors, and that is our strength, and we are having this one. It is accredited, after establishment of 6 months itself, our Center of Excellence in the medical devices, that is called MDTF, Medical Device Testing Facility, was accredited by NABL, and it is re-accredited recently, some 50 days back. And this center is being used by government of Assam for calibrating, including AIMS Goutham in almost all parts of the Assam. We are happy to announce that we are doing the calibration. Once calibration is perfect, instrument is perfect. Once instrument is perfect, rate of generation of the data is perfect. When data is perfect, your quality of your treatment is also perfect. Now this is about the facility certification. 18 years back, IICT got the param 10,000 to virtual product, and param Bengaluru, param Padma, and now I have established Bioengineering for the drug discovery. The result is, this is about something description about it. This is the result about the PARP1 inhibitor, which is for the cancer treatment. This will happen, this is an enzyme that will repair the DNA also, especially in the cancer, this will be there. We are able to predict the metabolism of this particular enzyme when it enters into the human system. This is a patent, it is a technology that already transferred to 2 companies. This is about the number of center of excellences we have, and apart from that, we are not confined ourselves only to the basic research or applied research, and we are also interested to have Atmanirbhar. Where from it will come Atmanirbhar? We have got the Biolite Incubation Center already in the phase 1, 32 graduates, 32 candidates have been graduated, some of them from IIT Goutham. And this is another one is NITI Aayog sponsored program at the Incubation Center, where prosthetic hand, and I am very happy to share with you, there is a eye cancer will be there, and ultimately I will be lost, and with Chawla, Dr. Mrs. Chawla, head of the department of All India Institute of Medical Science ENT, she joined hands with neighbor Goutham for developing 3D printed eye for that. Now, in case after removing that eye, if you fix it, this one, people feel it looks like a normal eye. So social stigma will not be there. Some kind of a societal applications of 3D, even in this one. There is a startup also in Aditya Incubation Center. Same topic and all. So finally, what I want to conclude, there is a future hope of this one for interdisciplinary, and this is forecasting of the AI will be a beautiful solution for replacement of the reducing the mortality and morbidity. Pharmacoengineering will be a ray of hope. It is only the light in the public health sector in coming 3 decades, and Aditya Incubation Center and Bioengineering certainly they will be inspiring to the young minds whose ideas can be conceptualized in my compound. Thank you very much. This is my holy place, neighbor Gautham.
So in this talk, I'll discuss about a couple of developmental activities that I was part of over the past few years. The first is on the life extension of a dual-phase zinc niobium alloy, which is used as pressure tubes in a pressurized seawater reactor. And second is on the indigenous manufacturing of thick section reactor pressure vessel forgings for upcoming pressurized water reactors. And a couple of activities which are ongoing. One is towards the development of accident tolerant fuel plant. So for this, we are developing these coatings on zircaloy clad, which is basically a zircon alloy. So these coatings are made through cold spray process. So for that, we want to understand the deformations in the zirconium alloy, the substrate itself. For that, we are developing a constitutive framework. And as a consequence of this work, we were able to develop a facility for precise high temperature dynamic testing. So it is a Hopkinson bar which is modified to perform precise high temperature testing. And then we developed a biaxial creep testing facility for tubular components. This is particularly for cladding applications where we want to understand deformations during internal pressurization of the clad tube. So the motivation of the first one is that so these are these cooling channels which are like 6 meter long channels inside which the fuel is posted, and the heat generated by the fuel is taken away by the coolant going through these channels. So this is a channel which is enlarged here. So we have a pressure tube inside which you have a fuel bundle, and the coolant going through takes away the heat. And because of the internal pressure, there is a hoop stress acting on the pressure tube, which is about 120 MPa, and the temperature is about 300 degrees Celsius. On top of that, there is neutron irradiation. So these conditions lead to what is called as irradiation-induced creep and cause an increase in diameter of the pressure tube. So this leads to a phenomenon called as coolant bypass, which leads to inefficient heat extraction, which has autocatalytic effects on the performance of the reactor itself. So there is a critical diametrical strain which basically limits the reactor life. So this component, the pressure tube, is a life-limiting component. If the diametrical strain, the increase in diameter of this tube increases beyond 5%, the reactor has to be shut down. And that actually causes a tremendous loss in terms of the economy, and that requires a shutdown period of about 12 to 18 months for complete replacement of these cooling channels. And so if this diametrical creep resistance is improved, we could extend the life, and top of that, we have an improved structural integrity. So there are about 13 such reactors are being constructed. So if we have such a property, we could have better structural integrity. So therefore better safety. So the premise is that how do we improve the diametrical creep resistance in this effect? So this is a section of the pressure tube in which these tubes, this material has an hexagonally close packed crystal structure, wherein you can have textures such that you can have basal poles aligned with the diametrical direction, transverse direction, or you could have basal poles aligned with the radial direction, which is the thickness direction. So in one case where we have basal poles in the transverse direction, we would require harder slip systems to activate, and which leads to better creep resistance. In case of basal poles parallel to the thickness direction, the loading axis here is the hoop direction, which causes prismatic A slip to activate, which is a softer orientation and results in a poor diametrical creep resistance. So a strong transverse basal texture would basically increase the diametrical creep resistance. And the current the previous understanding was that there was not really a good understanding basically on how during deformation a particular texture can be obtained, and in this particular alloy you have two phases, alpha and beta, one is HCP, other is BCC. When you deform the extrude these tubes at this temperature domain, you have this particular beta phase which affects the texture, and the know-how of how this beta phase affecting texture is something which needs to be studied. And only based on this, the extrusion parameters can be tailored so as to obtain a strong transverse basal texture in this particular alloy. So we have conducted hot deformation studies at different temperatures where you have different beta phase constraints. So as we go to higher temperatures, we have higher beta phase constraints, and it has been seen that at low temperatures where beta phase constraint is low, we have a strong basal texture in the compression axis. As we go to higher temperature where the beta phase constraint is large, we have a strong transverse basal texture, that is alignment of prismatic poles with respect to the compression axis. So these are the inverse pole figures which demonstrate that you have strong basal texture at low temperatures. As we go to higher temperatures, we have a strong transverse basal texture. And in the beta zirconium, the texture components are not changing as a function of temperature. So the first question was that whether the occurrence of this transverse basal component has any link with the texture in the beta phase. So through Burger's orientation relationship, we have shown that the 111, which is the texture component, deformation texture component beta, aligns with the 11 bar to 0, which is forming here at 800 degrees Celsius. And also that one of the 001 axis within this Burger's OR aligns with the 2 bar 1 bar 1 0. So both these components tend to give rise to this transverse basal component. So whereas at low temperature you have a typical deformation texture component forming. So by using thermodynamics and crystal plasticity simulations, we have shown that there is a sequential transformation of these phases from alpha to beta, followed by transforming back to a softer alpha orientation, leads to formation of this particular 2 bar 1 bar 1 0 component. So by understanding this mechanism, we were able to tailor the extrusion parameters and explain why we have a strong basal texture forming in this particular alloy. So the extrusion parameters are so tailored that we had a strong compressive state in the radial direction, which would basically translate to a transverse basal component. So with this, we were able to achieve a higher transverse basal component in the modified route. So, and we have determined the properties with respect to tensile, which clearly indicate that there is an increase in strength without affecting the ductility much. And more importantly, it is a creep property which basically determines the life of the reactor. So for about 40 years of operation, the creep rate should be less than 4 into 10 power minus 11 per second in this alloy. So the estimated creep rate at the operating temperature for the newly modified route alloy is coming to about 5 into 10 power minus 14 per second. And this is for the thermal creep part. There could be slight increase due to irradiation, but it would still below this particular value. So these tubes are now installed in some of the PHWRs and they are being monitored for their change in dimensions. And this is the first study which basically use the sequential dynamic transformations to engineer transverse basal texture in a dual phase alloy. And also that this study gives the mechanistic link between dynamic phase transformations and texture development in the two-phase alloys, which are could be applied to titanium alloys as well. And another objective was to develop thick section reactor pressure vessel forging. And at the time, there was no industry which was capable of manufacturing such large forgings. So these are the reactor pressure vessels which could have diameters ranging from 1.5 to 4 meter and thicknesses ranging from 340 to 750 mm depending on the capacity of the reactor. So our work was to establish at the lab scale, the processes which can simulate the industrial forging. So one of the process which these pressure vessels undergo is the hot working, where we have upset forging as well as ring rolling. And these processes, after completion of these processes, there are several heat treatments that are required for the achieving final properties. So with respect to hot forging, we had developed a processing map by doing straight compression tests. However, for simulating the forging operation, during this the temperature drops, right? So we started forging at 1200 degrees Celsius as a consequence of cooling. The flow stresses could rise. So to simulate that, we had carried out this step deformation test. And this is the forging hot deformation map where we have established the forging conditions. And this is a step deformation test result, which basically indicates that at a temperature closer to 120 degrees Celsius and below that the flow stresses rise significantly. And we have demonstrated the lab scale the forging operation of this reactor pressure vessel steel, and we have suggested that the forging operation should be stopped when the temperature comes below 900 degrees Celsius. And these are some of the snapshots taken during the actual forging of the steel. And the properties after final heat treatments were found to be meeting the ASME guidelines. And this particular work supported the first ever production of thick RPV forgings in India for the pressure seawater reactors through an industry research collaboration. So another interesting work that is going on at our lab is to develop accident tolerant coatings on a fuel clad. The motivation is that during one of the accidents, Fukushima nuclear accident, there was this particular reaction which led to generation of hydrogen, and this caused huge explosion of the reactor top plate. So the idea is to develop high temperature coatings that resist high temperature steam oxidation, and one of the coating materials is the max phase, which is Ti3AlC2, and these are like hard particles which upon interaction with the clad itself deform the clad. So we want to understand deformations within the clad and to optimize the properties for cold spray coating itself. So to determine that, we need high temperature dynamic behavior of the zirconium alloy, and also there is no constitutive framework which could accurately predict the anisotropic flow behavior for HCP metals. So to perform high standard experiments, with at high temperature in a precise manner. We had modified the Hopkinson bar setup where we have a gas gun at the rear end, which basically sandwiches the sample just before the wave passes through the sample. So both the guns, gas gun one, which basically propels the striker bar, and the transmission bar, they both trigger at one time and ensure that the temperature drop during the test is quite minimum. So overall contact time of the sample with the bars has been reduced to less than 15 milliseconds. And this resulted in a better test reproducibility. So this is the bar that has been developed at our division for carrying out high temperature test. So the other part was to develop constitutive framework for anisotropic flow behavior. So what I mean by anisotropic flow behavior is that when we deform material in two directions, you have different flow behavior. And this primarily occurs because of the changes in the microstructure as a consequence of choice of different deformation modes. So, and typically to model such deformation behavior, intensive crystal plasticity models are employed, and these are not so suitable for cold spray process modeling, where we could give simple we can develop a simple constitutive framework. So, and also that at high strain rates we have lower sensitivity of the flow stress to temperature because of what is called as viscous drag effect as a consequence of phonon disintegration interaction. So by taking into these accounts, we were able to develop a model which can accurately predict the anisotropic flow behavior as well as the viscous drag effect. So to model such anisotropic flow behavior, we typically use this physics-based model wherein the thermal component of stress depends primarily on strain rate and temperature. However, in case of HCP materials, it also depends on strain as a consequence of change in texture, and which basically changes the deformation modes. So by taking that into account, and the main change in texture occurs because of the evolution of twins. So if we can model how twin fraction evolves, we can model the evolution of flow stress. So by taking those things into account, we were able to modify the anisotropic flow behavior. And at high strain rates, we have this viscous drag effects coming from dislocation phonon interactions. And by estimating the drag stress as a function of temperature, and by determining the drag stress as a function of strain rate, we were able to predict the high strain rate behavior of this HCP alloy. It's not just the flow behavior, but the rise in temperature. Yeah, just maybe 30 seconds. So it's not just the flow behavior, but the increase in temperature during the high strain rate testing is also well predicted. So this work basically led to development of a setup for precise high temperature testing, and development of a constitutive framework which can be utilized for cold spray coatings. And this is the final slide where we have developed a setup now to estimate the biaxial creep properties of tubular component. So this tubular component experiences internal pressure, and that causes deformation due to a time dependent phenomenon called as creep. So this is a setup which we have developed at our lab. Here, most importantly, for materials which have hexagonal crystal structure, we need to estimate the effect of loading, which is basically through internal pressurization. You have this biaxial loading, whereas in case of cubic materials with random texture, this kind of testing is not required. But for hexagonal materials, this is quite a mandatory setup to accurately estimate the creep properties. So with this, I would like to summarize my work.
Thank you.
So we have utilized these sequential transformations in this fuel phase alloy to engineer transverse basal texture for enhanced creep resistance, and we have developed we have enabled the manufacturing of thick section preservable forgings through the lab scale studies and demonstration, and we developed this particular facility for high temperature dynamic compression and a constitutive framework for HCP alloy and the biaxial creep setup for tubular components. I would like to acknowledge my collaborators.
I will be briefing about a topic on advanced magnetic materials, translating research into real world impact. Here I will be presenting you two case studies that I have involved in. One is high induction iron nanocrystalline alloys. This is right from TRL 1 to TRL 9 what we have did. And next one is our recent 18 months work, iron nitrate based rare earth free magnets. And all this is possible only because of our institutional support, our directors and my seniors who made this platform so we can thrive. So first we are moving from less carbonized society, or we can go for more electrified society in which the magnets are the indispensable part for them. Among the magnets, we can see here, this is the banana diagram which shows the lowest coercivity, the best soft magnets over the period of time. The amorphous and nanocrystalline alloys are the superior soft magnets existing at the present time. And because of this, a especially on all these newer technologies like solar, PV or EV, all these soft magnetic materials are increasingly used nanocrystalline alloys. Right now, India is importing close to 600 crores of iron amorphous and nanocrystalline alloys. And what is their next demand? The demand, either it is an electrical transmission or electrical conditioning. In both the things, it is an universal demand to have high performance and size reduction. To have this materialistically, you need to have low core loss soft magnetic material and high saturation magnetization. But in any bulk magnetic material, these both are conflicting properties. So you have to have a solution, and one of the solutions that we have went is that the established nanocrystalline alloys has low magnetization. So here we will plan to work on high induction iron nanocrystalline alloys, and that results will be showing. So this is a tentative development framework for any soft magnet. You have to reduce all the anisotropies, so you will end up with the soft magnets. In this work, we have did systematically that one. So the first step is that you have to develop an iron-rich amorphous alloy system, and this is the marginal glass former and the most challenging. When we have very high iron content in any amorphous alloys, and for this to balance this amorphization as well as the magnetic property, a large amount of phosphorus is warranted, which is much more challenging. We have optimized, and 15 alloys we have prepared as a continuous strips, which is 180 degree bendable. The next process is that this is a soft magnet material. Still, you can make it much softer when you have a nanocrystallization annealing. And this is the famous Herzer plot where you can magnetism and microstructure can be correlated. Finally, what we have to know keep in mind is that the nanocrystal, the grain size should be less than 20 nanometer. So your coercivity will be low because of this exchange bias, exchange effect. And next, your volume fraction should be higher. So the saturation magnetization will be higher. So I am just presenting how this alloys how we developed and understood an alloy where we could achieve both the properties. This is an iron 83 alloy system where when we have do the optimal annealing and we increase the phosphorus content, systematically we have seen this is a BCC alpha peaks soft magnetic in nature. We are seeing with phosphorus the peak broadening is getting broadened. So quantitatively with the phosphorus content we got the most desirable property. My grain size is reducing by half from 28 nanometer to 15 nanometer, whereas my nucleation density is increasing by order. And this is what very favorable, and these are the TEM results to confirm the grain size reduction in effect with phosphorus content. So when we went to understand this mechanism, we have calculated the activation energy for the nucleation process, then the growth process. We can see with phosphorus content, either it is phosphorus free or phosphorus rich, the nucleation activation energy is almost similar. So that is accepted because it is an iron rich systems, iron atom will come together to nucleate very quicker. But what makes phosphorus really beneficial is that it increases the activation energy for the growth. So especially during this amorphous to nanocrystallization formation, this phosphorus goes and sits at the interface along with the solute distributed boron and the phosphorus niobium. These three forms a core shell type of structure, and we will be getting a very low grain size with a very high nucleation density. And this we confirmed with the Herzer plot to understand the size dependency. That is the origin of this good soft magnetism. Then I'm just coming to here. Based on all these studies, we have developed the most optimal alloy composition with the most optimal magnetic property. Then we went to the next step. We have used commercial raw materials, ferroalloys. In industrial condition, we have produced two strips, continuous strips with variable thickness, and we confirm their amorphous precursor states. After doing the optimal annealing, this is 3000 by 3000 bright field TEM image. You can see all the nanocrystals, the uniform and dense distribution, of this material. Now coming to the next step, as I said, India is importing 600 crore worth of material. So we have almost non-existent of any player producing this nanocrystalline ribbons. So one such company approached us for the indigenous production, and keeping that there is huge cost for the setting up any vacuum induction furnace based processing, they have an air induction based processing. Right from the raw material selection, we designed a cover flux, then we improved the ingot, then we optimized the planar flow casting, optimized the annealing cycle. We have did complete optimization of this plant, and right now they are successfully producing 10 tons of fine metal ribbons with 97% pass rate. This is a recent technology that we have developed from enamel, that we have produced positively magnetostrictive ribbons, continuous ribbons, and used as a sensor material and make a complete package. We used to call MSS sensor magnets, and this is for industries, mainly for the structural health monitoring. Coming to this our recent activity, that is that rare earth free alpha double prime iron 16N2 magnetic phase. So this is at the very preliminary stage of TRL1 that we are working on it. Now coming to we all understood the importance of a hard magnet, but unfortunately commercially if you see in the mass market category only there are two magnets available. At the high end you have intermetallic neodymium, at low end you have a ferrite based ceramic material. There is no other material, magnetic material in the mass market category to fill this gap. So most of the time you have to use neodymium magnets. And this, we all know about the supply chain. It's a highly, the carbon footprint is enormous for this NdFeB magnets, and the low Clark number, it's scarcely available. So last decade has some acceleration towards identifying new or novel rare earth free hard magnetic phases. Among these phases, the one particular phase of interesting magnetic property is this alpha double prime iron nitride 16N2 phase. This phase has reported to have a highest magnetization, a theoretical highest BH value, and most importantly very simple elements, and this can be choice for the bridge magnets. And from a structural and magnetic point of view, iron based material, when we incorporate 11.1 12.5% atom percentage of nitrogen, it will place systematically and it will dilate the structure to a non-cubic tetragonal structure. And because of this non-cubic structure, it naturally makes it a hard magnetic material. So what we are trying to do is that we aim to synthesize this phase through alloying and processing step viable for mass production. Although we are at TRL1, this is our attempt. What is,
you have 2 more minutes.
Okay. The main challenge is that this phase has been synthesized in thin films, but it's not possible in bulk because thin films have high active nitrogen, and we don't have nitrogen as a direct alloying element. We have to go for ammonia gas nitrating, and you to maintain a strict nitrating potential. So our strategy is that directly instead of going for iron, go for an iron alloy, and the choice of alloying element should be an arsenic stabilizer. And this is our process schedule what we have did, and we will be going for an austenitic nitrating, a single furnace where we will do hydrogen reduction, nitrating and gas quenching in a single furnace, then cryo treatment, tempering, and just showing some of the results. From completely BCC, after doing an austenitic nitrating, you will see the gamma phase is more FCC because of the nitrogen and arsenic stabilizers. Then when we do the cryo treatment, first time we got this disordered Fe16N2 martensite phase. And this is the microstructural difference between the starting material, which is BCC, and this is the nitrate based material. These are the TM results. Very interestingly, we don't find any data in open literature of the TM for this material. So in fact we are also curious, and we are very fond. It is forms like the elongated rod precipitate type structures, nanostructures. So this is some of the work we have did, and right now we used to produce gas atomized powders both for magnetic as well as non-magnetic for certain oil and gas applications in our pilot facility. So doing this development, most of the facility we have developed ourselves. because there is no standard techniques to measure. So for mantle friction, we ourselves assembled the SAMR technique for tensile annealing setup, IR annealing furnaces, and we have indigenously developed a water-cooled planar flow caster to produce continuous strips akin to the semi-industrial scale. This is used. This is what used for both amorphous material as well as neodymium strip casters. Thank you.
Very good afternoon to all the dignitaries, my seniors and peers, ladies and gentlemen. I'm Dr. Pattapu, our Principal Scientist in Central Institute of Mining and Fuel Research, Dhanbad. And today I'll talk about some of our work on the mine-environment interactions. And some of the research questions that we asked is, what is the possibility of value-added product recovery from mine waste, mine water? So there's a lot of geochemistry interfacing with chemical engineering. And a lot of separation processes that we develop are in close collaboration with the industry. And also we work with the different government agencies like the Pollution Control Board to solve some specific problems. Today I'll only talk about two important applications and focus in the science. I will skip some of the slides so that I can stick to the time. But I'm also always happy to answer questions later on. So I'll quickly come to the problem statement. Now, today I'll be focusing on sustainable resource recovery and mine water treatment. Now, mine water is a very broad term. There are all the mines present very different challenges, and even within coal mines, there are different challenges depending upon different parts of the country where they're located. What is the composition of the coal and the strata? So, but what is common is the fact that I am showing some of the discharge data from the major coal producing companies of the country. These are huge amount of water that is generated, and resource recovery is a secondary part. Whether it has got value-added product, we can recover or not, whether it can point to some other secondary presence of some other things in the strata is a secondary problem. What I would like to draw your attention to the fact is that this is a huge amount of water, and typically mining areas of the country are regions where there is acute water scarcity. So that makes it very, very important for us to first treat mine water. And when I'm talking about treatment, it cannot happen in isolation. We have to study what is the interactions with the environment and how the pollutants are coming, and how to also kind of develop intelligent mining practices. So therefore we work in collaboration with different departments across our organization and outside. Now, so every mine is different. There are different contaminants. Now, one particular problem that I would like to specially address today is the problem of the acid mine discharge. Now, acid mine discharge is a problem which typically affects the coal and the metal mines, which contains high pyrite. We are focusing here on the acidic mine water that emanates from the coal mines. Now, Indian coal, we are blessed to have less pyrite per se. Mainly in the northeastern parts of the country and also in the lignite mines of Gujarat, Rajasthan, we have a high amount of pyrite. Now, this pyrite, what happens? It reacts, there is a ferrospheric cycle, I'll talk about it, and it releases hydronium ions, iron, which runs a cycle, and that makes the water highly acidic. Also, what is important is the fact that in a lot of these mines, there are certain contaminants which are not exactly contaminants. In some cases, their concentrations might be good enough to merit recovery. So can we develop some specialized membranes? Can we develop some specialized treatment techniques to recover them? Now, the solution that I'll talk about is we worked on different membrane separation systems and also, like in the earlier slides, on process development. So one particular technology that I would like to tell you is forward osmosis. Now, it has been talked a lot. Now, we are especially trying to make some membrane-based crystallization out of it. And what exactly is forward osmosis? So we are all very familiar with reverse osmosis, RO membranes that we use. This is the exact opposite. So here what happens is we have two solutions with different concentrations separated by a semi-permeable membrane. One of them is a wastewater or the feed that we are trying to treat, Another is the draw solution. A simple chemical solution, sodium chloride, magnesium chloride. We artificially put that solution so that across the membrane there is a concentration gradient that is created. Now the membrane is a semi-permeable membrane. So it only allows selective passage of the solvent. So all the solute is restricted. Now it makes sense for us to use this for mine water, which is in a layman's term a soup of different contaminants. So if we can have a very effective dewatering technique, then we can have, and also something that is not very energy intensive, because like I've shown here, it uses the concentration gradient. So therefore, it needs very, very less energy. Typically, it should not need any external pressure, but we do apply a small amount of pressure to increase the speed of the process. Now, we have tried to experiment this and also combine something called membrane-based crystallization, where the membrane will promote heterogeneous nucleation, and also we can add some chemicals. So we can combine chemical precipitation and separation, very selective separation and isolation of some targeted products. And now I'll show you how we are using that. So before that, of course, we are experimenting with the science, and also if we are trying to develop prototypes, these are the different engineering optimizations that we have to do simultaneously. So here I've tried to show the different stages of process development along with our different stages of research. So we've tried to work with different systems and different parameters we optimized, and also like, the flux, the concentration polarization. I mean, concentration polarization is a problem that affects the membrane system. So here, since we have two solutions, one is the feed and one is the draw solution. So there are two membrane interfaces. So there are two different kinds of concentration polarization that we are dealing with. And we had to also characterize that. We also had to see the flux decay, and over a period of time, how can we get a sustained flux. Of course, with backwashing, with pre-treatment, when we are moving from lab to the field, what are the challenges, all of that we had to work on. And also we have experimented like how to minimize the energy consumption, whether we can add some mechanical force like a piston, and what are the kind of modified membrane cells we develop so that they kind of have less a pressure drop, and we experimented with different feed spacer layouts so that these can be portable systems as well as large scale systems. So in some cases, if we have like drinking water based concentrations, we can directly get them in small mines, and also in larger mines to treat the problem of acid mine drainage. Now, so when we were developing initially, of course, we validated it for different contaminants that we found in the mines, for phosphate and nitrate, and we optimized them. We also optimized flux and downstream. So forward osmosis produces a dilute draw solution which needs subsequent purification. So downstream we had to optimize between osmosis and nanofiltration. Now, so once we were armed with all of this knowledge, we thought, now let's go to the field. Let's target acid mine water. So this is like an incremental research. So we started with understanding of the problem, and especially in the northeastern state of Meghalaya, we did a lot of field work, and so, like I said, a lot of geochemical interventions. And so these streams that you see, these pristinely blue streams, these are very highly acidic. Their pH is around 2 to 2.5, which makes them unsuitable for any kind of human animal consumption. So this is exactly 3 hours from Shillong, the outskirts of Meghalaya, and despite the abundance of water resources, tankers had to be deployed, which is ironic. Now, what we found was, typically in the acid mine drainage systems, you have high sulfate because iron pyrite is responsible. You have high iron. There are heavy metals. So it's a complex matrix. Now, another interesting pollutant that we found was aluminium. So aluminium, in some cases it is present in the acidic mine water, in some cases it is not. Now, this kind of gave us an opportunity. Calcium aluminium sulfate is entering that. So we thought, let us try to use our recovery based insights, what we did at the lab level. So whether we can recover calcium aluminium sulfate by dosing calcium sulfate, some calcium carbonate, whether we can form, whether the sulfate is appreciable to form that compound, sulfate and aluminium, how to optimize that, and with that we kind of started that work. And we also, of course, paired that with membrane-based separation. So we were able to precipitate calcium aluminium sulfate in the form of product, which is ettringite, and also treat water. Now, to understand, of course, we integrated a lot of geochemistry to understand where the heavy metals are located and how they will exactly precipitate under different conditions, because when we are dealing with these mine waters, typically they will change around the year, and also as the mining happens, and in the northeastern states the mining is not very scientific, I'm sorry. So different parts of the strata are exposed. So when we are dealing with a real system, the challenge becomes appreciable.
Okay,
I'll try to quickly summarize. So we optimized nanofiltration, and this is in like one graph I tried to show like how the combination of chemical addition with membrane separation, how we are able to remove iron. We removed aluminium and sulfate, and that sort of formed the ettringite. And also one of my students, she worked on this modeling where before we went into field, we tried to see like what are the total chemical consumption if we are moving, and how viable it is, of course. And we were supported by the Meghalaya Pollution Control Board. They gave us huge quantities of water back in Dhanbad, which we tested, and also we used their laboratories back in Meghalaya. And this is the crystallization process of it. I'll skip for the time. And this is another application where we kind of use that for the steel industry effluent treatment. Now, ammonia, cyanide, and phenol are pretty well-known contaminants, and there are quite a few studies where they remove it or in isolation. So, Ministry of Steel had a very specific problem. We had to develop a zero liquid discharge system for the steel plants. Against that problem statement, we started working. And also whether we could actually valorize the steel slag, whether we could use some of the steel slag as composites and couple that with membrane-based separation. So we were able to recover ammonia through some zeolite-based systems, and we were also able to selectively separate that, and at the same time we were able to remove phenol and cyanide, two main contaminants. And this is in the near future. So what we are trying to do is, our lab work is done. We have almost any pilot scale systems, and we also have incremental grants, one from DST and one from Ministry of Steel shortly. So we are going to feed. This is the schematic diagram of the small pilot scale plant, 100 meters per hour. We'll be setting that in the outskirts of Shillong, so which will produce ettringite and also treat the water. We haven't been able to go to drinking water standards till now for the acidic mine water because of the cost involved. That water would be fit for agriculture, which would also be helpful because that entire region tankers are being deployed at the moment for any kind of water source. So this is the plan, and some very interesting work. I just take 1 minute. So while we were developing these membranes, some crazy idea came to my mind. It's electron hole recombination for water splitting is pretty well known, and electrolytic loop and a lot of research is being done. But somewhere in my mind, I thought we can make some membrane composites through very thin membranes where we can actually tackle the problem of the electron hole recombination for water splitting. This is entirely different from the previous work that I've shown. So I went on a Sai fellowship in USA where we made these small reactors and we developed these membranes mainly through a technique called electrospray coating. And we were able to develop some low-cost materials, which I wouldn't say the hydrogen production is very competitive with the lab scale compared to the electrolytic technologies, but the cost is a fraction, and that gives us hope to continue this work. And we were able to study some into the mechanism of the electron hole recombination, and this is one area apart from that main work which we would also like to take up in the next couple of years. So yeah, with this, like, that ends whatever research and teaching, and this one area is very close to my heart. So although the research and teaching, they take all of my time, this is an outreach program for CSIR which I am doing from my lab since its inception. Initially I was very, very scared it will eat into my research time, but I was able to balance that. I wouldn't say it is not eating into my research time, but I believe I was able to reach the grassroots and a lot of students from very underprivileged schools, and it's a joy to treat them and also to meet people who are very curious without the resources you and me we have always had. And also we are collaborating with Stanford University and a couple of other universities to develop very low cost study tools, and I believe this is one aspect which is making me a better human being and giving back to society. So with that, I would like to end my presentation.
Thank you so much.
First of all, thank you, Eileen, for this very special honor. It is a pleasure to be here and be sharing some of the work that we have been doing in our group. We are trying to understand the processes of cancer metastasis and drug resistance, which are two major clinical challenges that have still not been solved. So metastasis, as many of you may already know, is still the major cause of all cancer-related deaths. It largely happens with this fantastic set of three ways that we have in our body called blood vessels, through which cancer cells are able to spread to different parts of the body. If you look at the dynamics of this process, it's actually a very, very inefficient process. More than 99.9% of the cells that leave the primary tumor are thankfully not able to metastasize and grow other tumors in the part of the body. Now, why we have still not solved the challenges of metastasis can be understood through this analogy. So this is from the Harry Potter series, but you can replace it with any series that you might have seen. If I just give you two pictures, one is close to the first scene of the first movie and the second is close to the last scene of the last movie, and then ask you, tell me what happened in between, we have no way of guessing what has happened. This is where metastasis research is. You have a primary tumor picture, you have a metastasis picture, you have no information on what happens in between. You don't even have information whether the people shown in this are the same as the people shown in this or not. Because you don't profile the entire tumor, you only take a small biopsy from a given patient. So these questions are still very poorly understood. When cancer cells leave the tumor, why do they leave it? Do they leave as single cells? Do they leave as groups? Which organs do they stop by? When do they settle in? And so on and so forth. Now, if you look at the other major challenge, which is drug resistance. So what are the different therapies that are there in the clinic so far? We started with surgeries, then 50 years later came radiation therapy, another half a decade came chemotherapy, another 4 decades came targeted therapy, and now we have immunotherapy. But unfortunately, despite all these different options, what seems to happen for a large set of patients in the clinic is that initially the tumor mass comes down when some of these combinations of treatments is given, but then it does begin to come up. Cancer recurs, it recurs in the same organ, it recurs at different organs. The time still depends on which cancer and what treatment we are talking about, but this is still a major problem. And why we have not yet solved this, we have some hypotheses. So for example, let's say if you were completely able to profile a tumor and say these are the different kinds of cells that are present in a tumor, and you even had therapy for all of them. We are not there as a community yet at this juncture, but even if we were able to do that, we are still taking many assumptions. The one assumption we are making is that every red cell, for example, will respond identically to the given concentration of a drug and will have one and only one outcome, which is cell death, which is clearly not the case. Cells respond differently to the same scenario. We are also assuming that no drug is able to induce the switch to go from a red to a blue cell. It will either stay a red cell or die. That are the only possibilities, which is also not true. There have been scenarios that cells can actually switch back and forth. The third assumption we are making is that the unit of treatment is a single cell. The unit of cancer is a single cell, which is also not true because cancer operates as an ecosystem. Cells are cooperating with each other, exchanging all different kinds of signals with each other. So all the different therapies that I showed you, which we have currently in the clinic over the past 1.5 centuries, they reduce cancer to a static, dumb system. But in reality, cancer is a dynamic, adaptive, complex system, and we need to understand from an engineering perspective what are the different dynamics, these concepts of non-linearity, reciprocity, and multi-scale behavior that we need to better understand to have a better strategy in terms of treating patients in the clinic. So that is where computational models become very important, because then you can map out the different possibilities that the cells might be going through. So let me give you 2 quick case studies. This is in the context of melanoma, which is skin cancer. You can see patient prior to treatment, there are all these lesions on the skin. 15 weeks later, some of these lesions disappear, but only 8 weeks later, in presence of the therapy, these lesions come back. So cancer cells did not disappear, they were just hiding. They had some acquired a different state, which was not permissive to the drug, and then as soon as you remove the drug, they were able to grow back again. Now, what seems to be happening is that these cells are switching back and forth, and that is why this is a moving target, because we don't even have the rates of transition, and how those rates of transition depend on the different perturbations that we're going to have. So at one snapshot, you will only get one profile with no information on what it could evolve into. Now, have also been studies that there are some cancer cells which can either grow very fast or they can migrate very fast. So there's initial reports that cancer cells can do one thing at a time. They can either metastasize but not grow, or they can grow but not metastasize. But more recent studies have shown that actually both cells can do both things, vice versa. So you put some cells in a mouse, initially they go and then they grow, and vice versa. They can switch back and forth very, very actively. So we wanted to understand what is the bare minimum network of different molecules interacting with each other that can explain some of these observations, that you have multi-stability and cells can switch back and forth as well. So this is, after extensive reading of the literature, these were some 5 nodes out of large possibilities of 30,000 or so molecules that we identified, and said this is the way, this is the network wiring diagram that experimental biologists over multiple decades have painstakingly mapped out. Now, what are the possibilities of the outcomes of these interactions? So we convert this interaction into a set of differential equations and then solve those differential equations over multiple initial conditions and parameter sets. And then we notice is that, so even if you were to classify each expression level or node level as on or off, you still have 2 to the power 5 possibilities. You still have 32 possibilities here, on or off times and so on. But when you look at the dynamics, there were actually only 5 possibilities, broadly speaking, because the dynamics, the regulatory networks actually constrain the dynamics to allow only for a specific set of interactions. And what are those dynamics, or what are those 4 states, So broadly speaking, if you look at how invasive a cell is, or how proliferative or dividing a cell is, these are usually antagonistic properties. So each cell so what initial experiments had identified is these 2 extremes, the cells which go don't grow and cells which grow don't go. But there is actually an entire spectrum of possibilities, and there are these cells which are somewhere in between, which have the capacity of doing both things at the same time. Now this is just simulation. Let's look at real data. Let's look at cells grown in the lab, and cancer cells taken from patients grown in the lab, and let's look at cancer patients' data themselves. Again, you notice this strong antagonism as was predicted by a model. This is all bulk data set, so you're basically taking 20,000 cells or even more and then measuring an average level. If you look at single cell data, which is becoming more and more predominant these days, again you see the same behavior. So what we are saying here is that in a large dimensionality, there are some signals which are actually connected to each other, which have a mechanistic basis with why we see these signals and not any other pattern that can be explained by these kinds of dynamical models. So the next question we asked is that this only tells the possibilities that cells can exist in different states given the interactions. And in this scenario, we have not considered the impact of a drug. What happens when you add a drug on top of it? So again, we take the experimental data that is available and look at the control cases versus the treated cases, and again project them on the same dimensional axis that I was talking about in the previous slide. So in the untreated cells, you have these cells which are proliferative but not invasive, and also invasive but not proliferative. But when you look at the treated cells, this subpopulation disappears. This subpopulation is no longer present. Now, just looking at the static picture, you cannot say whether this was an induction or this was a selection that was happening. But you can look at other combinations of data. So instead of treating with one drug, let's look at data treated with 2 different drugs together. And now you begin to see new cell states which were not there prior to treatment of the drug. And what are these states? These states are that cells are more invasive in nature. So the treatment of drug itself is pushing a subset of cells to become more aggressive than what they were prior to treatment of the drug. Of course, some cells are dying. We don't have the numbers here, how many cells die and how many cells switch. But this is certainly a possibility which has been ignored by all the clinical ideas so far. This is not unique to melanoma. Let's look at ER-positive breast cancer. Breast cancer is the most common cancer, and if even in that there is something called estrogen receptor-positive breast cancer, which is the most common type of breast cancer. So the general idea there is that
Mohit, you have 2 more minutes, please.
Thank you. So in that example, also what we observed was that the ability to metastasize and the ability to resist drugs, they were actually strongly coupled to each other as a consequence of these interactions. And these interactions, individual regulations were reported by the literature, but what was not observed was what is the outcome possible as a consequence of all these different interactions. So when you do that, you again see that cells have these 2 different states. Cells can switch back and forth between these states, and this is what exactly we found when we looked at the experimental data, that when you make cells more migratory, they become drug resistant, and when you make cells more drug resistant, they become migratory. So in both scenarios, so the clinical implications of this is, let's say a patient is being treated with this drug, which happens in the most common scenario. Some cells in this cancer are becoming more aggressive, more metastatic as a consequence of the therapy that is being given. So how can mathematical models impact cancer treatments? Just summarizing this, and why should we be looking at this? According to the latest estimates, in India, 1 in 9 people are likely to develop cancer in their lifetime. That is the estimates from Indian Council of Medical Research. And the numbers that we see here of the number of cases that are going to happen, we still don't have better therapies out there. So we clearly need to better understand how, instead of just looking at it from a reductionist perspective, which is what cancer biology has done for many, many decades, we now need to integrate all that information and to use mathematical modeling as a tool to accelerate the aspect of drug discovery, accelerate combinations of drugs which can be given to specific patients, or certainly belonging to the Indian diaspora as well. So one question can be, why can't we just try all different FDA-approved drugs? This is what was done in this particular study, where they had more than 100,000 combinations that they tried, and only 5% of them were actually doing a better job than individual. So, and this is just in the lab. This percentage goes very, very close to zero when you actually go to patients. Because what you do in the lab doesn't mimic what happens in the mouse, and what happens in the mouse doesn't mimic what happens in the clinic. So clearly this this sort of trial and error approach is not really going to take us there, and this is very laborious in terms of time, infrastructure, as well as personnel that is needed, which is not necessarily possible for the kind of numbers that we are looking for in the very near future. So mathematical models can help understand what different trajectories cells are taking to adapt, pinpoint the vulnerabilities of these states, identify different combinations of drugs in a much less resource-intensive manner, and then of course suggest combinations that can be tested in the lab. So that, I'll just summarize what we have observed in different scenarios is that the dynamics of cancer cell gene regulatory networks, these are all multi-stable dynamics, so cells can switch back and forth spontaneously, and drug can also make things worse. And mathematical models can be one important tool which needs to be added, because usually in our education system in class 10, when the roads diverge of biology and math, they rarely come back, and it's very important for it to come back eventually to be able to solve these questions of societal impact. So digital twins, which is something that the industry standards of many engineering disciplines are slowly beginning to make their way into oncology as well. We need to collect these data so that we can make these processes much more efficient for patient care. With that, let me thank the funding agencies and the team of collaborators and students, and also YIEA for this very special honor. Thank you.
Thank you.
So today I'll be talking about my research area, which is on sky convergence, a unified framework for scalable monitoring of various sustainable agriculture and forestry related practices. So what do I mean by sky and earth? So sky, as shown in this particular figure, so sky is basically monitoring using the non-invasive sensors, basically satellites and drones, and earth is basically the sensors or the observations from the field. So basically it may be from the crowdsourcing mobile camera or actual sensors deployed on the farm. So the overall philosophy behind this is, can we effectively combine the various modalities so as to achieve the precision at scale. So the key philosophy is precision at scale. So this is just my background. I won't go into much of the details. I did my bachelor's in agriculture engineering and then did my master's in geoinformatics from IIT Bombay, and I've been working with this group, Digital Food Initiatives Group at Tata Consultancy Services since last 12 years, and received a number of research projects since 2013. So I've been fortunate enough to work on participatory sensing, remote sensing, some of the drone projects and the hyperspectral sensing at the intersection of AI. Moving on, so before going into the specifics of my work, I'll briefly touch upon what this overall program is about in the Tata Consultancy Services. So I'm a part of a research group at TCS, and I'm working in this group called Digital Food Initiative. So the overall philosophy is the digital AI-enabled platform wherein the data from various modalities, you can see the various modalities from Sky and Earth. The data from various modalities will be acquired. So you can see the 4A model, right? So the underlying principle is 4A model. The first is acquire, which is the data acquisition from various modalities.
then analyze that data, turn that data into insights using some sort of AI, ML, or possibly now the generative or the agentic AI based modeling. As soon as this analysis is done, can we do some advisory, convert that insights into the real usable outcome, maybe farmers or some other stakeholders, or in some cases actuation as well. So the overall philosophy is about 4A model using the sky and earth convergence, and this could be applicable across various sectors. So this is about the program, but my work is mainly focused on agriculture and forestry. Some of the other guys are also working in livestock and aquaculture as well. So now going into specifics of my work, which is the sky and earth convergence. So as I mentioned, we are fusing modalities of different types, maybe satellites, aerial photography, drones, or maybe data from smartphones or the ground sensors. So the main motivation for combining this data is whoever who has worked on satellite data must be aware. There are only certain things which are possible using satellite data, but you can achieve the scale. And when it comes to drone, you will get very high resolution data, or when we are capturing the data, let's say from the mobile phone, about the particular paste or disease, you will get more granular picture. But if you are capturing the data using mobile phone, it may not be scalable because you can only capture data at certain points and instances only. So the motivation was, can we optimally combine the data sets from multiple modalities to be able to achieve greater accuracy, and at the same time can you achieve the scale? And while fusing that multiple modalities, I have come up with these 4 approaches. So this was the novel part on which we have filed a couple of patents. So how can you combine the data? So it again depends from, or it will vary from objective to objective or problem statement to problem statement. In some cases it will be sky guided earth intervention. In some cases it would be round away. In some cases it would be sky and sky. In some cases it would be sky earth. So depending upon the problem in hand, we'll decide which route we would like to take. And again, there is some sort of optimization coming into picture. So overall, objective of this particular project or this particular framework was to develop and optimize this framework, which can integrate data from multiple modalities for accurate, scalable, and transferable estimation. So specifically, whoever is working in the agriculture or forestry sector, there are many AI ML based models are getting developed. You will see lots of models, lots of algorithms are being developed, but one of the challenges that is being critically faced is the scalability. If you are developing models for Indian region, are they applicable for US or Western geography? Or vice versa is the case. So how can we have the transferable estimation of all those parameters? That is what I was focusing on, to be able to generate that verifiable evidence, which could be used mainly from carbon credits compliance or sustainability incentives perspective. So what I'll do is, as a part of today's presentation, I have 3 to 4 use cases, but probably depending on time, I will focus on depending upon the time permits. The main focus was how can we monitor regenerative agriculture practices, and this particular figure basically shows the typical Indian agriculture cycle. So basically it starts with monsoon, you'll have first cropping season, then you'll have some brief period, then you'll have another cropping season, and then you'll have again some brief period. So during this entire agricultural year, I would say, which starts from June of this year to next May of the next year, during that particular period, there are many practices which are happening or which are carried out by the farmers. Many of these practices have drastic impact on the sustainability. I'll be covering today about the tillage and the cover crop. So I'll go to that particular slide now. So the first use case which I'll be focusing on is the sky and earth convergence for tillage detection. So I think many of us are from the agricultural families only. So I'm sure everybody is aware of what tillage is. Basically the interculturing operation, and there's a belief that it will increase the production, or to some extent that is true as well, but depending upon the intensity of the tillage, it will really hamper the soil organic carbon, which will emit carbon into the atmosphere because of that mobilization of the soil, and because of which it will lead to GHG emissions, right? So there are various practices which will lead to those emissions if those are not handled properly. So the intention of this particular research was, can we detect the amount of tillage or the intensity of tillage that has been conducted by the farmer over those fields? And the examples are like minimal tillage. So minimal tillage is like you're only doing the tillage only once
before the season, and then you can see extensive tillage. There are 4 different types, there are 4 instances in which the tillage has been done. So if you are carrying out extensive tillage, which means you are contributing a lot more to the GHG emissions. If you are carrying out minimal tillage, you are contributing less, and there is no tillage as well. There are many farmers who are practicing that. So can we identify that the amount of tillage that has been happened over farm by the farmer? Can we do that using the satellite data? That was the attempt which I done in this particular use case. So basically, the core philosophy, which has not been attempted earlier, is so the prior art was mainly focused on whether the tillage was done or not. It was a binary decision, and even when it was done, that was also not attempted. So what we tried to do is when it was done and what kind of tillage it was done. So whether it was a no tillage, minimum, or the extensive tillage. So we have gone into that details, and to be able to come up with that level of granularity, we basically use the soil color based features. So soil cell color chart is one particular chart which basically talks about the various shades of soil, and depending upon what kind of tillage is being done, that variations you'll be able to get that. So which was not attempted earlier. So what we tried to do as a part of this particular research is, can we detect the information or the signals which are proxy to that soil color chart, which could be related to the tillage. So that was the attempt which was done in this particular study, and we were able to achieve. So the outcome of this one is, so this is the small region which I am showing, but this has been done almost for one entire province of Canada. So this particular study was carried out for Canada and India as well. So the map which I am showing here is for Canada. So for each field you will be able to see. Yeah, sure. So for each field you will be able to see whether the tillage was happened and when and what kind of tillage. So for this particular use case, I was able to achieve 86% accuracy, and the combination of multiple satellite data sets helped me improve or capture the tillage signal in a better way. The second use case is again a cover crop. So this has a very much significance mainly from the US and the Western geographies. So in India, mostly there are 2 or 3 agricultural cycles. So there is a very limited period in which the crop is being fallow, and there is no scenario of snow or something like that, which was there in US and Europe. So what happens is in US and Europe, after the main cropping season, probably after October till the next year of March, during that 6 months, probably the soil is fallow. And if the soil is fallow, it is exposed to the atmosphere, there are chances or there are proven studies that it will emit again the carbon from the soil because of many reasons. So the attempts are being made that can we have some sort of cover crop over that agricultural area during that fallow period. And many companies are giving incentives to the farmers to have that cover crop. But while detecting the cover crop, again there are certain challenges, because cover crop is some sort of crop. As mentioned here, it may confuse with main crop, because main crop is also there. Then there are dense weeds as well. For certain things, there is snow as well. There are famines. So there are lots of uncertainties, and the combinations are there. So to accurately detect that cover crop and the duration of cover crop, we have come up with this 2-stage approach, wherein what we are doing is we are separating that entire signal which is captured about that particular agricultural field into different buckets, and each bucket will be tagged, as I will show in this figure. So this particular signal is for one field where you can see there is a main crop, then there is fallow in which there is again snow, and then there is again main crop. Similarly, there is another scenario which is a little complex scenario, when there is a main crop, then cover crop, in between there is snow, for some period there is a grass as well, and there is main crop. So detection of that was really challenging only using the traditional approaches. So we have come up with this 2-stage approach to be able to accurately detect that. And for this use case as well, we were able to achieve more than 90% accuracy. So this was about the agriculture. This is maybe the last slide I talk about. This is again another classic example of how optimization can be done. So this was done again in 30 states in northern states of India, wherein what we are trying to do is, using the satellite data, it's not really possible to detect the exact baseline decisions. But we would like to achieve that by some sort of optimization. So what we did is, using the satellite data, we only detected which are the hotspots, which are the areas which are under stress. As soon as that is detected over those fields, then we move to the drones and the mobile camera based imaging. And using those specific areas, So instead of flying the drone over the entire area, then we only focused on certain areas when there is really a stress. Over those areas, the drones have been flown, certain pockets of that tea state, and then using those drones images were processed to identify certain pests. Again, on the other side, it was a mobile camera based captured images wherein we are detecting using the image processing algorithms what kind of pest is there. So this way, we are able to detect the specific locations where spraying needs to be done. Again, some sort of optimization going into picture, by which you are saving on the cost as well because you are not flowing drone over the entire area. At the same time, you are detecting very precisely at high accuracy because using drones and mobile camera images, you are getting very high resolution pictures by which you are able to specifically detect that. And ultimately, the outcome is you are only spraying at the areas where it is really needed. So, kind of spraying. This is another example of style convergence wherein I developed this approach for tea. So, I have some more slides, but I will not go into details. Some sort of work on forestry as well. This is again recently published in the National Journal of Remote Sensing. I have estimated the forest EGP, which has direct implication with carbon emission and carbon sequestration potential. So this has been done for entire Indian geography, and the results were quite good. Yeah, maybe I'll skip this some of the achievements and recognitions. So this is the overall coverage. I have not worked on all of that. Couple of those mainly from the sustainability, forestry, and the farm monitoring, and the rest of the use cases were mainly from overall group's perspective. Yeah, I think this is on my side.
I'm Dr. Richa Karmakar. I'm an assistant professor at IIT Madras. Some of the things are not visible. I hope that my video should work. So I am working on, in my lab, we are working on point of care microfluidics for rapid and comprehensive disease diagnostics. So this is one of the area we are focusing on. So basically I like to present, like we were developing different kind of microfluidics for different kind of disease diagnostics. So today I will focus only on two problems specifically. The first problem is that detection of antimicrobial susceptibility of microfluidic sensor by electrochemical impedance sensing. So what happened in case of UTI, or if you go for any kind of bacterial infection, and if you if the person having any kind of bacterial infection, they go to the doctor, and then doctor actually take the blood or urine and immediately prescribe some broad spectrum of antibiotic. So which is causing a very heavy antibiotic resistance of the bacteria. So when the doctor sent these samples to any of the pathology lab took almost like 48 to 72 hours for giving the report. So what is the utmost requirement is that can we actually detect this antibiotic susceptibility of the bacteria on a very short span of time, and then can we say that whether this bacteria, first whether the bacteria is there or not. So it will actually eliminate whether the infection is due to the bacteria or it is due to the virus or some other infection. And similarly, because sometimes with the viral infection also doctor prescribe the antibacterial, which is not required. Can we do some sort of a faster diagnostics of this antibiotic susceptibility? So for that, we use the comparatively simple matrix, and we take the disease that is called urinary tract infection, which is the second most common infection evolving in a complicated cases due to the antimicrobial resistance. So what we develop is, we call it as electrochemical microfluidic device, as EMUD. So this is a very simple microfluidic device and a low cost, where we are actually having the glass slide with screen printed, this is a screen printed electrode, which is, this electrode is made by the carbon ink, which is again like a cheaper, and on top of that we put the microfluidics device, in which we have the inlet and outlet, in which actually we are we are introducing the bacteria in inlet, and the outlet channel is just like for the flush out, and then we are attaching the electrochemical device. So basically the workflow is that This is the electrode, which is that screen printed electrode. On top of that, the microfluidic device is there, and then we introduce the urine sample or the sample matrix, in which the bacteria, if the bacteria present, the bacteria will adhere to the substrate, and then using the electrochemical measurement, which is like basically between two electrode counter and the working electrode, we are actually putting the potential and we are measuring that what is the resistance coming from. So if the bacteria is higher, the resistance will be higher. So basically here the plot, this plot is called the Nyquist plot, which is our readout. So this Nyquist plot will tell us whether is there any kind of like a deviation from the control sample, which tell us whether the bacteria are there or not. And then if we introduce the antibiotic, I'll tell you the story a little bit later. So this is how the device looks like. It looks a very simple device. And if you actually, so this is the 0 hour plot, and if you incubate and we introduce the bacteria, and we are, as I said that this is a Nyquist plot where we are concentrating on this RCT value. So if the bacteria grow on 3 hour and 6 hour, you can see the deviation of this RCT value over the period of time. And basically bacterial concentration and the metabolite production is higher, then the RCT value is reduced. So this is how we are doing. So this is the sample we are introducing into the microfluidic device, and then we are closing the channel so that the bacteria, we are giving some 30 minutes time so that the bacteria can adhere, and then we are actually flushing out the sample matrix. So whatever the bacteria there in the sample will adhere to the substrate, and rest of the urine sample will flush out, and then we attach the that potentiostat, and then we are getting this measurement. So basically and then as I said that we can say about the susceptibility testing also. So if the bacteria whatever present in our sample are like susceptible with the drug, because we introduce the drug as well, then you will not see any RCT value changes. But if the bacteria is resistant, then you can see the RCT value changes because the bacteria are growing. In this case, there is no bacteria growth. Here in this case, the bacteria are growing because it is a resistant with antibiotic, and that's why you can see the RCT value changes. So similarly, we have done the delta RCT value, the difference of that RCT value based on the susceptible and resistance, and you can see that when the bacteria is susceptible, we are getting a very low RCT value, almost negligible. And in case of the bacteria, if it is resistance, we are getting the very high difference of the RCT value, which is depicting over here. So, then we had tested our device with a different kind of antibiotic, whether it is because the bacteria is not only susceptible or resistant on one antibiotic, so we tested with a different kind of antibiotics, and which is verified with that classical plate experiment, which usually in a pathology lab they used to do it, and we verified with a human urine sample also. So initially every test was done with the our lab scale based solution, and then we later use the actual urine, and then we are trying to say that there is no hindrance of the sample matrix, and basically we are able to detect the almost like 500 CFU, which is like really low. When the doctor prescribed it as a UTI or detected as a UTI, the bacterial load usually 10 to the power 5 CFU per ml. So in that we are able to detect 500 CFU, which is really good. So what is the different features? We are able to detect a very low concentration of the bacteria with the 3 hour. We have a direct detection of the bacterial growth. It is a very low cost carbon electrode, so our device, one chip which is like replaceable, this chip is costing only 150 rupees as per the lab scale. So if you go for the mass production, it can go even lower. So it is the support portability, ease of use, and works directly with the crude sample. So after that, I will just highlight one small work where we were as we were working on urinary UTI. The next question is that whether our device is capable enough to work with the blood, because the blood also have the similar kind of bacterial infection. So can we put the blood and detect using our device? So actually we tried that. It is giving us a very huge background noise. So basically what is telling us that because the blood has RBC, WBC and many other plasma, all the other sample matrix, which is actually giving us a very wrong signal. So that's why it is very utmost requirement to remove the bacteria from that RBC, WBC. So that's why we were, and it is not very easy to remove the bacteria because bacteria is very tiny, and when it is coming from the blood sample, the bacterial load even lower, actually 10 to the power 3, 10 to the power 4, like that. So here we are using a very, it's a bit complex, but it is giving us a very nice result. It is called that acoustofluidics, where we are actually putting some kind of like acoustic field over here. So this is how this acoustic field using that signal generator and amplifier in this microfluidics channel, the acoustic field are generated. Because of this acoustic field, we have the node and the antinode. So the bigger particle will come over here in the node, and the smaller particle will go towards the wall side. And this is what we are getting it. This is a microfluidic device, and we are able to separate the bacteria and the blood, and this is actually done with the real blood. So we started with the real blood and we did the separation. So you can see that the very thin line, so this is a video, so you can see that the RBC are coming over here, and we are able to, and no RBC are going over here. Bacteria you cannot see with this magnification, but at least you can see a very focused line is coming from here, from the middle. So then, yes, I will just quickly finish. So we are actually working on another major problem, that is the human papilloma virus detection. So cervical cancer. So cervical cancer, which is caused most of the cervical cancer, the prevalent cervical cancer was caused because of the HPV 16 and 18. This is a human papilloma virus. So this is cervical cancer is the second most prevalent cancer among women in India, and actually even till now even the vaccine has already come. The government has not deploy it as a mandatory vaccine. So because of that, almost like 82% cases of the cervical cancer are coming out, and because of the unknown things, the people doesn't aware of that they might have been ended up with the cervical cancer. So that's why the screening is a major challenge. So people are not doing the screening properly. So that's why we are trying to develop a screening kit for that HPV 16 and 18 detection. So because only the 2% Indian population are screened. So we have the in-house method of the isolation. So first what we are doing is, we are doing the DNA isolation on the paper-based substrate. And then from there we are using that loop-mediated isothermal amplification, that is a lamp amplification. And the next step we are doing this detection using that different kind of fluorescent staining. And this is the device in which you can just directly use this paper device inside. You can insert it and you can see whether the signal is there or not. So basically we use different kind of paper. I will not go into details. So we are using different kind of paper to say whether which one will give us the good yield of the DNA, because DNA is very much required, and we are getting that CH1 and which is giving us a very good DNA yield. But CH1, that chromatographic paper, is not giving us a very good amplification. So that's why we go to that G113 paper, and then we have done the different amplification also. You can see that the chromatographic paper giving us a very low amplification. So almost like a G113. So we have to do different kind of, this is a verified lamp amplification on the gel matrix to say that whatever we are detecting are getting the pure lamp is amplifying or not. And then we actually This is actually the device after we are done with the lamp amplification, we are doing the detection, in which you can see a very nice, if it is non-template control, which will be the control, and then the positive control, you can see that it is actually the fluorescence is there, the fluorescent signal is there on the edge. So basically this kind of data will tell us, in case of a non-template control, the fluorescent is everywhere. In case of a positive control, the fluorescent is kind of on the edge side, which will tell us whether the HPV is there or not. And we had tested with the several patient sample this device. So right now we are almost reached as 200 patient sample. This whole technology we deployed in IOG, which is that gynecological hospital. It's a government hospital in Chennai. So we deployed our whole setup in government hospital, and we are getting everyday samples. So we almost reach 250 detection, among which we are getting almost like 14-15 positive already. So that is what the final thing. So in our lab, we were working on that in vitro diagnostics. Again, this is one type, like one part of my work we are working on. So we are developing others microfluidics device to understand also the cell-cell interaction, cell-substrate interaction. So in vitro diagnostics, we were working on that electrochemical based microfluidic device. We were working on that HPV detection. Also, we were working on different kind of paper-based microfluidic device for other kind of metabolite detection. Either it can be a biological metabolite, or it can be the different kind of chemical component which is coming from coming from the environment. So that is what we were developing, different kind of laser printed microfluidic device, and we are trying to do this different kind of other detection. With that, I wanted to thank my group. So many of my students were working on different field of the disease diagnostics, all of my funding agency, and with all of my collaborators, because most of the work which I am presenting over here with the collaboration of many of the professors over here, which is enlisted. And finally, I wanted to thank INA for giving me this opportunity to talk about my work in this stage. Thank you very much.